picture diagram, this is kind of how it looks. You've got a document in the middle. This is how we're going to do all the synchronization. You've got connections between devices, right? And then that document is going to link to blobs. I'm not going to go into deep detail on the structure of documents and the data model and stuff on that. We'll cover that in the workshop. If you want to hear more about that, that's after this. But the thing that I want to sort of just like, I just want to cut to the chase and give you a demo of what I mean by sync everywhere. And hopefully that'll help drive a lot of this home and make it a little more palatable. And so, do I have everything set up? This is a good question. All right, so I'm going to show you some stuff. And by new places and far places, I'm going to start in a fun new place on my phone. And so you won't be able to see this, and I just got too close to this. This is fun. But what has just happened is my phone has created a document, and it is now here. And that document's ID is 3UP. Cool. And when it did that, it also sent it to IRO Cloud, or IRO.network, which is our cloud backing service. Cool. So I'm going to jump into that document. I'm going to look at my connections. I have a whole bunch of connections, one of which is direct. And you'll immediately realize that we are, well, you won't immediately realize, I will tell you that this server is in the United States, and we are currently in Istanbul, and my latency is 146 milliseconds. That is going to be relevant. That's not a great ping, but it's still worth looking at. So I'm going to take this thing. This thing has a photo taker hooked up to it. And so, like, I'm not really selfie game, but we're going to do that. And that shows up there. And we can see my stupid face. Hey, cool. And, like, I think the bit that's fun is, like, sorry, camera people, I'm moving around. I won't move around, sorry. I can't move around. But it's like, kind of quick, right? And great, we can sync. These two devices are connected. Oh my God, go away. We've got phone to IRO.network. Cool. This is a cloud connection. This isn't hard, right? So let's do something more complicated. Let's bring in, okay, now I have to do a little bit of juggling. Host 2002, I think? Yes, cool. What I'm going to do now is I'm going to share a ticket. A ticket is our way of getting stuff, and I'm going to bypass this write warning for reasons that you'll see in a second. I'm going to go over here, and I'm going to say, hey, yeah, let's replicate this to IPFS. And what you're immediately going to see is this thing joins the document, sees everything in it, syncs that, pulls that data, puts it on IPFS, and tells us about it with these hashes. So I can now go this, localhost 8080, IPFS. Most of you, hopefully some of you have played with this before. And we can see my stupid face again, yay. And again, the thing that's fun here is it's synced. So it shows up and then it replicates it, right? And this is what we mean by lots of new places. We've got this incredible new paradigm when you can suddenly do synchronization in a meaningful way. Now we have this new kind of substrate that lets us do this compute in the loop. And the bit that's really fun was the hard part. Right now, my phone and my laptop have a much better ping than the cloud network, and we actually have a solid direct connection between the two of them, right? And so that's the tough bit, and we've focused really hard on getting an incredible, consistent connection between devices as we go. And this is what we in the peer-to-peer and direct networking space really care about, right? And so I think from there, it'd be fun to try and stress this a little more. Anybody got a laptop? Yeah. All right, cool. I'm going to need you to, I'm hearing zippers. That's a very, cool. This is, I need you to do this. So you're going to, if you go to iro.computer/docs/install, it'll give you a copy-pastable version of this. And then I need you to join a Discord. Sorry, because that's how I'm going to get you a ticket. And what you're going to do is you're going to, where you saw ticket, yeah, follow these things and copy, where you see the enver for ticket, you're going to have to copy paste the thing from the Discord if somebody can get that. If you have some other way of transmitting that. The install is, well, you could copy, well, you can't copy and paste because you could manually type that, or you can do iro.computer/docs/install. This is going to be fun. We'll see if this works out. Rudiger, you already have this on there. Did you check to make sure that that works? Oh, hey, everybody. What's up? Oh, I'm sorry. You're all looking at this screen. I need to give you this access. My bad, my bad. Yeah, we're going to stress test this thing live. We're going to see how it works. Particularly my phone. And we'll talk about why I'm very confident doing this in a second. But I would love an audible gasp if you actually manage to sync anything or get to the dock keys. So dock keys will let you see it, and then dock watch will do to see if we can actually do something fun. But anybody made it yet? Version 0.6 of Iro? No, you need 0.10 or higher. Actually, not higher. 0.10 is the latest. You need 0.10. The ticket is in the Discord. So I pasted it here. I can paste it again. Boop. So you're going to do dock join. And this switch flag is going to just it will set the console to actually pay attention to that document in particular. It is in the Discord. So if you copy paste this. Yeah, I can try to make this bigger, but I don't think you're going to be able to type that. Unusual activity detected in Iro. Which one of you is spamming us? Can we? Yeah, I don't know. Can I do a paste bin? Oh, you're going to do this. Oh, okay. Oh, I see. You're going to do the text recognition thing. All right. Ah, smart. Can you stop? Anybody else need me to pull that back up so they can do the really cool text bit? No? All right. I'm going to join myself. Actually, no, I can't because you guys need this pulled up. So. No. Do -- mode auto. Or you must be compiling from source. Huh. Yeah, okay. You got it. We got a thumbs up. Okay. I'm going to take a photo, and we'll see if you get the new photo. I'm going to take a photo of this wonderful thing. I don't know what this is. Oh, the clicker. Yeah. Let's see if it's synced here. Nice. I heard an audible gasp. We've got some work happening. Cool. All right, I'm going to leave this up. I'm going to keep talking. Feel free to, does anybody need an extra couple of seconds with this up? Or feel free to play around. Yeah, Iro start is the thing that turns on your local node. Okay, cool. We're going to keep moving. Thank you, everybody, for helping stress test this thing. I will take one more photo of how much time I have remaining, which is that much, and see if you can pull that guy up. But I think the bit that is, hopefully you can see the value here of sync, right? We have a bunch of new paradigms that emerge from this. We have this fun little replicator sitting in a loop. I can also do stuff on the actual console. I can affect this from multiple parties. This one has a write key, so I can do hello world. And our little IPFS replicator will then dutifully copy hello world to IPFS, which is super useful, I guess. Maybe not useful, but hey, whatever. But keeping with this theme of syncing anywhere, we have this all set up in a sense that gets us lots of languages and lots of access to a lot of different places. So currently, Iro ships in Python, Go, Rust, and Swift, and we're adding more as we go. And when we mean an SDK for this, we mean that Iro actually can run natively in that runtime. So you can run pip install Iro, and you will do Iro new node, and you will have a node running in the process that is currently there. And the huge advantage of that is imagine yourself in remote machines, in Python scripts, in whatever. It is much faster and easier to bring Iro into your process. And this is what we mean by sync anywhere. We can take it onto phones. We can take it into applications. We can take it into all these different spaces that makes this whole system far more useful because you can now start to bridge other technologies together, right? On top of that, we were demoing a little bit of this, which is this IRO.network piece. And this, for us, is two things at once. One, it's a product. And two, it deals with the issue that you run into in peer-to-peer systems where people turn their phones or laptops off. And so this is a high availability system that lets you push and pull too. It is a full SaaS service. It has a free tier that I'm using today to show you this thing, and it has a paid tier that you can use to get more concurrent connections, bigger storage, and all the like. But most importantly, it's not required. You don't need IRO.network to use IRO at all. And there's lots of use cases that really show up when you really focus the whole thing around connections like this. In particular, like this notion of sneaker nets, which is kind of an abuse of the term because sneaker nets usually are actually just USB keys. But we at Number Zero all the time are using IRO to debug IRO. We generate a lot of logging information, have to send logs to each other, and it's just this like giant pain. And like a bunch of you are now have IRO on your machines, thankfully. And so like I need to get you the slides for this talk. And so at the end of this, I will just put this in and paste a ticket for you to grab this whole thing and be able to pull the slides for that talk using IRO. And so we use this all the time, and it's like a really classic, simple use case when you have these fast, direct connections. Next bit, I think that is also quite fun, are gateways, and this idea that like we see from IPFS land. And Rudy, did you send me that thing? Awesome. So this is as an example of a gateway in IRO parlance. And so what we're doing here, hopefully this one works. Did you give me a new ticket, Rudiger? Oh, cool. Do I have a node running? Oh, let's find out. Oh, I have to restart my gateway, don't I? Oh, no. Cargo run. Yeah. What? Oh, I'm in the wrong place. There it is. A lot of stuff flying around today. But see if that'll figure itself out. Oh, this would have been made fun of demo. There we go. Cool. Gateways. This is actually not the sync side. This is just a straight blob of 5 gigs of content that I am not caching on my machine. This is currently fetching from Rudiger's machine, which is right there in the room, and we're streaming that from his machine to mine, and I can seek, I can play. Yeah, totally. Get the full experience of what are we watching? Some Internet Archive piece. Something we checked to make sure that we had something that was public domain before doing this. But yes, a distinguished French scientist who is having. But like the joy of this is that this is just the thing that's distinct about what you're probably used to from IPFS space is the ticket bit that we were showing actually includes dialing information. And the thing that was being shared, as you can see, this URL has shifted. This is a piece of a collection. And so this is very similar to the way you think of like a UnixFS directory. We're actually seeking into the whole hash and then getting a specific bit out of it. But we're also incrementally verifying this as it is being transferred. And so this is doing the whole trick of like if somebody had constructed a false version of this incredibly enthralling public domain film, we would know about it as it was streaming immediately. We verify it both on send and receive, which is like a very nice property where if you have data corruption on either end of the wire, you'll know about it. Another wonderful use case. And then the one that we really care about, which is apps, right? Like the ability to like build apps on top of this is kind of the whole point. And so here I'm just showing you a document being joined so that you can actually just kind of use IRO.network as a data model explorer. And so on the right, this thing is just using a document to store its information or the state of the app. And this could easily be synced across a whole bunch of people, right? You have all of anybody joins that document, they're gonna have this wonderful live synced thing. But you also have all of those tricks that we showed at the beginning of this where we were ingesting to IPFS, but that's a generic solution. You can write software that comes in and, oh, cool, somebody uploads photos, you can do the photo resizing in band as part of the process and dump the results of that back into the same document, right? When you have sync as a fundamental substrate, you get all of these new tricks that show up. And we think that's what really drives this whole system into brand new territory, right? And so by millions of new places, like just in the process of this conversation, using my phone, I created like 25 IPFS hashes and synced them and sent them both to IPFS and to IRO, right? And this is what we mean by sync. I think the sort of substrate of being able to sync anywhere is like it's this incredibly valuable, useful addition to things. The fun thing about IRO is like we're not trying to replace your Postgres database. We're not telling you to rip out whatever you're currently using. Strap it on top and use it to glue between stuff and open up new things that you couldn't do before. And I think that's the really exciting thing. When you have sync, all of a sudden you can say, oh, I'm going to pull this data from that system and this data from that system, harmonize them and do something interesting with it. I'm going to do heterogeneous compute where different nodes in the network will have different roles depending on their strengths and weaknesses, right? And so really you can sync anywhere. And I'm doing this mainly just to get a dig, but you can send him wherever you want. And the idea of having this magical capability to just any node declares that everybody who's interested gets the thing that they have just published instantly completes the sort of read-write cycle. And if you think about where we've been in IPFS land and in content address data for a long time, we've kind of been, in my mind, we've been in read-only mode for a long time. I add to IPFS, I get a hash, and then someone consumes it, and then you run into this problem of, okay, now what? How do we change it? And once you get the right side and you have synchronization in the loop, everything, it doesn't get a little faster, it gets a lot faster. You can make a lot more data a lot quicker. And I think that's the really exciting bit. And so that's what we're up to. This is open source. A bunch of you joined our Discord. That's great. You have a thing that you can use. You should totally sign up for the free IRO computer thing. You should check out our docs and start coming and hacking on this with us. It is early-ish days. A lot of this stuff is actually pretty solid at this point. Definitely lots to do, but we're pretty pumped. Like, I think this is like some groundbreaking shit over here. And so, yeah, thanks. That's kind of the whole spiel. I can take questions if anybody has any. Oh, apparently there is a microphone, so we have Russell and then Arachne. Yeah, sure. Thank you.
Thanks, Brenton. I'm just curious about the JavaScript support you have for this. Do you have any front-end libraries available that may also need support?
Totally. So on the JavaScript side, you mean the browser, or do you mean Node? Do you mean Deno? Do you mean what's your all of it? Do you want me to answer it all?
Any.
Yeah.
If any support, if it's Deno, that's great.
Yeah. So like obviously, not obviously, but just oh man, it's still playing. Good job. This is JavaScript and it's talking to IRO data. Mm-hmm. This is happening over a WebSocket and an HTTP API. And so, not great, but I fully intend to write and would love to work with folks on writing a JavaScript library that, for now, at least just consumes the HTTP API and then go a little deeper. If you're in Deno or Node land, we can do far more interesting stuff. And so that's where the core of this is all written in Rust. So WebAssembly becomes a very interesting and exciting avenue. And so the thing that we've focused on really hard for this whole project is getting the API to be completely consistent. And so when you do doc.new and you see this, you can see an example of how to do doc.new in the console, and then in Python, and then in Go. And the idea here is these concepts should be consistent, and the API should be singular, right? And so my answer to your question is let's go implement the API. Yeah. Cool. Ghazal, do you have a question?
Yeah, I was wondering sorry, I'm loud, I realize. The docs that you're syncing is like a flat list of key values, essentially?
Yeah, and so we should get into that. I can briefly speak to that, because it's a little more complex than just key value. It is a set of key, which is bytes, not UTF-8 strings, so you can do hashes in there or whatever you want in there. We can thank Rudiger for that insistence. The size of the content, modification timestamp, this is literally a wall clock timestamp, and the author. And you'll notice a special thing about the author. Oh, and the value is always a hash, right? And so that is the full schema of a document, and that's locked in the protocol, basically. The thing that really matters is if I tried to set photo as a prefix, you'll see I get all of these yellow because I am currently author this, which is kind of hard to see. And these entries were written by some other author. And so we are in a shared namespace, and think of it as a table with like different keys. I can't actually overwrite that. I can overwrite my own stuff, right? And so I actually wrote hello into here earlier. So if I go...
and if you have two different computers, they're both you, I assume, does that mean individual computer can only overwrite things that it edit or across your computers?
Yeah, so we deeply encourage folks to use, we call these authors. And so you can have not just multiple authors you can have as many authors on a node as you want. And so it's kind of like identities, but it's sort of more a substrate for that. And so you can think of it more as like a per device identifier. So my author key on my phone does not move to here. And so that's how we distinguish folks.
I guess what I'm getting at, like, how do you deal with conflicts? I
With
assume that you might have a concurrent writes.
Yes, so
And somehow you need to resolve it.
the idea here is it's kind of drop dead simple. It's just wall clock timestamps. And the timestamps are consistent to the individual authors because the authors are local. And so you can do last writer RINs combinations of these things, but sometimes you just don't deconflict them. Like we can have multiple hello keys and values, which is a little weird and a little, you have to kind of do some getting used to. You can also just write a query that says, give me the latest write of hello and just suffer from the idea that you're going to have clock skew. And so if two people write really close in time, but it's intentionally messy because that's the nature of the thing, right? But you have the tools you need to disambiguate. Question 2, yeah.
Semi-related to that, is there any notion of access control? And I mean, how can I create a document that nobody else has access to, even if they have the...
Hi, thank you.
Yeah, no, sorry, yeah.
Super confused. So we kind of have access control, sort of. We have read and write, right? So I shared read access with all of you. I didn't give you write access, but it is, yeah, I know. It is whole document. Right now, you have no way of cutting up the subspace. This is all based on a actual protocol called Willow, actually, which we are an implementation of. And it has a spec that I think wonderfully marinates between the world of UCANs and OCAP, and there's work to be done here. But we at least have the baseline. I can just share a read key and a write key. We plan to get more sophisticated on that. It's really hard to get this right, and we got to figure, getting the boundary on this is going to be something we do with users.
So they are loud. So I remember earlier this year, maybe it was last year, there was some excitement because what you were doing with Uro was kind of separating from the whole bundle of IPFS sort of protocols and systems. And I never quite managed to wrap my head around which bits still connect and which bits are different and how that actually affects how you might, use IPFS and this together. So
Totally.
would you...
I can elaborate on that.
Yeah,
absolutely.
give the 10,000 foot kind of view.
So these are the 3 layers I want you to think about conceptually. You would call connections libp2p in IPFS land. You would call blobs IPFS in IPFS land. Documents, I don't think that there's a proper allegory for that. That may be, like MFS, I'm not going to. Yeah, maybe. Connections for us is completely different. We have done a total ground up implementation of our networking stack. It is not compatible with libp2p. It is written on top of Quick and the notion of something called a magic socket, which is a set of technologies pioneered by Tailscale. The reason for us doing that, this whole demo hinges on direct connections. My phone and my laptop must be able to connect to each other. It's not a probabilistic thing, it's these devices. And so we optimize for that solution. Blobs is easily the most compatible layer. You can have any hash function you want in IRO as long as it's Blake 3. Yeah, and so but that section, when we did, to speak to the compatibility, the way that I was actually doing the IPFS translation layer, you can see some of this where the hashes on here are actually the same. It's actually just ingesting the hash and doing an equivalency where we punch it into Kubo and get out the other side. If that thing is less than a meg, the hashes will actually be equal and like completely the same. And we have a couple of users who have like their systems, just all of their blocks are below a megabyte, often because you're doing IPLD work. And so you just get fully equal systems. When you start doing photos and arbitrary size data, then things are going to be different. But so we lose compatibility there. We lose compatibility at the, so there's like, I think the blobs plus connections, there's a really strong influence of IPFS. There's some bridging work that we can do, and part of the point behind this demo is to show that bridging work is like trivial, right? Like I could just leave this running for folks and have the IPFS bridge rocking, right? On top of that, all of these, I should also mention, all of these records are signed by the author, so you have an actual signed attestation that this was what it says. Sorry, I've got a minute 30, so let's go 10. Yeah.
Can you talk a little bit about, so each node also has an HTTP server which serves as some kind of like a local bridge, or no? Okay.
No HTTP server on the node's stock. The gateway that we showed is an example that you can run separately.
Okay.
And so this, and that's in our IRO examples repo, but like this thing that was streamed, that is, not streaming the movie anymore. Oh, still streaming the movie, yes. Is just like a bolt-on. And this isn't actually, this bit is just the blobs and connections layer. Okay. It doesn't have any documents, so. Yeah, so HTTP bridging I think is pretty trivial, and we have some great examples of it, but yeah. Oh yeah, we're at time.
So IRO is like there's IRO binary, but it's also meant to be used as a library very easily. So if you need something where you have an IRO node which combines the HTTP gateway, you can just take the two things, build it in a single Rust crate, and you're done. It's very simple to plug it together. But by default, we don't want it, because if you're on a phone, for example, you might not want an HTTP gateway, and nobody's going to need it, and it's wasteful to have it. And like having it and then disabling it, that's also not great, so it is just an external component.
Thank you so much, everybody. Really appreciate your time.
All right, everybody, we're going to take a slight little break as we move in for the next talk, for the next set of talks. If you want to continue the discussion with the IRO, B5 is going to be in the next room over doing the IRO workshop, over there, that direction, so just out and over. Please catch up with him there. We'll take a quick little break here, and if Will Scott is in the room, maybe I can get you to come, oh, there. We'll get you set up. And yeah, there's coffee down the hall. Go grab a snack, come on back, and we'll see you guys here in a couple minutes. Thank you. All right, let's get you set up here.
USB-C? Should we do the logo? Yeah, they said yes. Excellent. So my name's Will. I've been around Protocol Labs for a while. This talk is looking at the things that are happening with car files. And this is sort of an interesting intersection between data transports and file formats. We've had sort of an evolving role of CAR, Content Addressed Archives, over the last several years, where it's taking on some new roles and being seen as a viable solution for a range of things, where previously some of that was a block store of how you would keep data around in a permanent way, and then CARs came in as a way to export and re-import data. But then we've also started to see CARs as a viable transport mechanism as well, and they're starting to play a broader role in data transport, and so there's a whole new set of constraints that are coming in, and that's leading to some further evolution of CAR files. So I'm going to go through sort of 3 different sections here. We're going to talk about the CAR file format as a refresher. We're going to look at what's been happening around a couple different IPFS implementations in terms of using CAR files for data transport. And then we'll talk about sort of the stuff that's still up in the air that's getting worked on as that continues. CAR files. CAR stands for Content Archive, or Content Addressed Archive, or whatever you want with a C and an A and an R. It mirrors in many ways a tar file. If you look at sort of the structure and the design that goes into it. This is a diagram that you can find on the ipld.io website. But essentially, we've got a fairly small header at the beginning. That's the orange bit on that slide, which just says this is a CAR file. That has an optional root of the DAG or the data that's put in there. And then after that, you just have a bunch of blocks. And the blocks are serialized as a uvar int of the length of the next thing, the SID or the hash of the data, and then the data itself, and then you just keep repeating that. And that's CAR-v1. That's been around for a while. It's easy enough to export in that format. It's easy enough to re-import in that format. So we've got this great thing called a CAR. We've had it for a little while. Subsequently, around Filecoin era, we realized we were going to be storing large CAR files in Filecoin that were like 30 gigabytes. And if you had a 30 gigabyte archive of blocks that were all under 2 megabytes on disk, and then you were being asked to take one block of 2 megabytes and send it to someone, it was not the most efficient to either have to take all of that data and put it into a block store in order to get random access, nor was it great to take the whole 30 gigs as you got a request and put it into a block store to find the 2 megs that you needed and send it. And in fact, you really wanted some sort of index to do a direct seek to that 2 megs of data so that you could efficiently send just that 2 megs of data back out. And so that led to CAR-v2. CAR-v2 is a subsequent iteration of the file format that adds the ability to put an index at the end so that you can get more efficient random access reads over your CAR file. It has a set of kind of weird nuances to handle backwards compatibility. Namely, there's a pragma at the beginning that says, this is a CAR-v2, it has nothing in it, close, so that old CAR-v1 readers will close cleanly and not panic. And then it starts up again and says, here's all my blocks of a CAR-v1, and then it puts an index. So CAR-v2 knows how to handle this. CAR-v1 exit cleanly and doesn't do something weird. There's libraries for it. It's not too much worse than CAR-v1. The main thing to think here is we added the ability to put an index at the end. We add also in that sort of v2 header / pragma metadata that happens at the beginning, the ability to get some future extensibility. So there were some fields in there that were sort of said, well, we'll put some capability bits so that we've got an option to signal subsequent things if we need to. And we've got a couple fields here that let us sort of indicate, that there might actually be more things in this header so that we can extend this header so that we don't have to make a car v3 when we realize there's some other thing that we want in a car file format. Like we did with car v1, for instance, where there was a single thing of version number, which turned out to not be enough to then extend things without the car v1 readers that already were implementations crashing. Cool. So that's a car file. Cars in motion. So you've got this thing that has some blocks, and then we decided, and this again came sort of out of Filecoin where you had these 30 gig car archives. People were just using HTTP to download the car archive and then restore it on some other person's computer, because what they wanted was the exact same bytes that someone else was storing. And so rather than going into BitSwap and sending those blocks individually and making sure you tried to get them reordered in the same thing so that you got the same bytes at the other end, or doing that same operation with GraphSync, if you just took the bytes in a car file and did an HTTP download, you would get the same bytes on the other side. And you didn't have to worry about actually understanding any of the semantics and making sure that you had the right depth-first ordering of your data or things of that nature. And so you could do a much simpler implementation through a direct copy. And so we suddenly started to see that there were all of these HTTP servers starting up, and that people who were doing data replication were just doing HTTP transfer of cars. At the same time, from the IPFS gateway with things like Saturn, we realized that as the IPFS gateway, you had this option between sending the picture of the monkey or the blocks with the SIDs that composed the picture of the monkey so that the client could verify that that data actually matched the root SID that it had requested. And so you could, if you were going to push the verification of the content that you were asking in a content addressable way to happen on the client and not on the gateway as a trusted gateway, you needed that metadata of how the data was chunked and the SIDs that compose that and the metadata SID of the file in order to actually do that full verification locally. And that starts to look a lot like the data that's held in a car archive of that file, right? There's not too much additional overhead, and if you were to car export your file, that's pretty close. You don't even really have to, like, I don't know, squint too hard to say, yeah, that's what I would like to have transferred over the wire to then do my local verification of this, because that's what happens when a local IPFS imports that data, is it's doing exactly that operation that we would imagine wanting a smart browser client to do. And so these two things led to saying, can we take and extend what an IPFS gateway is to have a trustless mode where we send something that looks a lot like a car, and in fact, let's just make it a car v1. And great. So what does that actually mean in practice? Well, to get a file on an IPFS gateway, ipfs.text/IPFS/Baffy yada 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 gives you a file. This is a slightly compressed thing of what's in that IPIP that says the format we're going to use is you can just say format equals car, or you can use a content header or an accept header to say that you would like to accept a car as your file format. And then we've got a couple parameters that we found useful in how you request things that you can use to scope the data that you're getting back. And so those two parameters, one is your DAG scope, and that is saying, I want this direct hash, please. And that looks a whole lot like a raw request that already was supported. You can say, I would like this entity, which is a weird thing that gets used a lot in practice, but is kind of messy, and is essentially saying, I would like this folder, but not all of the files in the folder. And so it has UnixFS semantics, which are a different layer of the spec, but is useful in practice. And then all, which is, I would like this whole DAG, keep recursing on links, give me all of this as a car. Okay? And then the second one was, web browsers keep asking for range requests because someone seeks the movie to halfway through, and the browser knows sort of how to deal with a movie and actually ask for a gigabyte into that movie. It would be great if we can get the subset of the blocks in the underlying file to efficiently render the movie from halfway through. And the server actually knows how to do that pretty well. We have, with IPLD, enough knowledge of offsets of things to actually give you the relevant blocks based on an inbound, I want this subset of bytes. And so we have this entity bytes defined, again, with UnixFS semantics hidden in there in order to specify that you want a subset of a file. So those were the two knobs that seemed in practice relevant to serving gateway request traffic efficiently that got encoded in this. There's a subsequent set of parameters that happened here as well, because, of course, people want more. So a subsequent IPIP 412 defines an ordering. Should these blocks be traversed in depth-first search order or breadth-first search order? So do you want your metadata at the beginning, or do you want it interleaved as you need it? Because different types of traversals wanted different orderings. And then secondly, if you run into the same block multiple times in this data, so it repeats the zeros a bunch because it's padded with a lot of zeros, should I be sending that block multiple times so that you, as the client, don't have to buffer anything and can do it in a purely streaming way? Or should I go for less data transfer, but the client is going to need to remember that there might be a block that's going to get referenced in a traversal that was sent way earlier in the traversal, and so you better have kept that around if you want to be rendering the file. So different client sort of memories and buffer sizes leads to whether or not they would like duplicate blocks to be sent during that traversal, or whether they don't want that. So these got added. The interesting thing about these is that they're getting sent in a different way than those query parameters in the previous part of the cars in motion. So rather than this being a thing where I set as a query parameter of I would like depth first, these now end up being a question of the ordering and the contents of blocks that come back in the car in a way that we want to differentiate them so that if they're the same content in some sense, right? Like if I ask for a subset of bytes, that's a different car file. But if I say I want the same car file but just ordered differently, it has the same blocks in it. And in some sense, if you cached one that's a different ordering but it's the same blocks, you might want that still. Like it's maybe less efficient, but it's the same data inside of it. And so that is cached is like a useful thing in some cases to differentiate on. So these were considered at two different levels of like differentiation of can this satisfy the cache versus is this a different thing? And so these actually go as preferences in the content type. And there's a two-way negotiation where the client, when it is saying what it accepts, says, I would like to accept a car with duplicates. And the server in its content type then responds, I'm going to send it to you with duplicates. And that two-way signaling in the query allows us to agree on these additional semantics or opt into duplication or a different ordering than default. So let's talk about the future. There's a few different IPIPs that are in discussion. IPIP 431 is extending that same mechanism that got used for dupes to try and add the ability to send some metadata at the end of a car. There's two things that have come up there. And so you can see here that, again, in your accept, you would say meta equals e of as part of your content type to agree on, I would like to send some e of metadata here. Or I would like to send at the e of, I may send some metadata. What is that metadata that you might want to send? You might want to send an error, like I'm stopping your car partway through. In an HTTP world, there's no way to say why you stopped the car partway through. If you both agree and the client now recognizes that it's going to get this little block of metadata at the end of the car transmission, that provides an opportunity for when something potentially stops partway through that you put this error JSON to say, hey, the reason I stopped was I couldn't find it in my block store. It also allows the ability for the server to sign the response, which is a thing that Spark is interested in verifying the ability to retrieve data. The second one that's happening is extending these traversals with a way to skip raw blocks. This is used to say, can I send just metadata, but not the actual block data? And so this provides sort of a scaffold that you can use in combination with sort of direct raw downloads in order to re-piece together content verifiability in efficient ways that are hybrid. So both of these discussions are going on IPFS specs. I think that's my 15 minutes. I hope you all are excited about a car future. Thank you. Woohoo!
All right, and you're taking questions outside or later. We're around here all day. All right, well, set up Vasily for the next talk about IPFS over storage. Thank you. Which cable are we at?
Just mirrored. Just a moment, we'll show it. Presentation on this display, it will mirror it to the screen. Hi guys, how are you after yesterday party? Hopefully you have some energy to talk about what we are going to present and have some time and energy for party tonight. I'm Vasily from Chinstack. I'm head of product and I'm going to talk about how we use Storage backend for our IPFS API implementation, especially for today's speech on IPFS Connect. First of all, a few words about what Chinstack is. Chinstack is basically a web-free infrastructure service provider. We run blockchain nodes for multiple networks, more than 25 different networks. You know, any popular networks that you can imagine, Ethereum, Polygon, Avalanche, Solana, Aptos, you name it. And we're running mainnet and testnets, and there is more than 50,000 nodes running around the globe for our customers, and we have almost 100,000 customers who are using our services. And besides nodes, which is our definitely a core business, we're also providing access to indexed blockchain data, when fetch all transaction and receipts from blockchain and giving access to this data over GraphQL interface or SQL interface, or we can just share your dump with this database file. And using this indexed blockchain data, we also have such services as NFT API, wallet API, token API for those companies who need that. And last but not least, of course, we are providing access to distributed storage over IPFS API. And let's talk a bit about how we did that. But before I will jump into that, can you share me who knows that IPFS is not a storage? Okay, like at least half of you know this. IPFS is not storage, which could be surprised for some newbies who came into this industry. But yes, IPFS is not a storage. IPFS is, for those who still don't know that, IPFS is just a way how to get access to your file. Yeah, how to find the file, how to find the object inside this decentralized or distributed storage system, and how to get information like when you can actually locate your file. And with that said, of course, you still need some storage solution behind your IPFS API. In much easiest way, of course, you can use local drives and just giving IPFS API to your local drives. But in that case, in case if you will lose this a server, a virtual machine, you will lose your file. And definitely you would like to have your file distributed, redundant, for long storage retrieval time, and so on and so forth. That's the reason why any company looking how to store your files behind IPFS API. And in the simplest way how we did that, Of course, in Chinstack, we have our user interface over web browser, and we have public API for RESTful API access. And behind this API implementation, user interface implementation, there is IPFS node, which is, a binary, a software that's expose your IPFS API. And behind IPFS node, we have multiple storage nodes, but you can use just one of them, but we have multiple because Chinstack service is a global distributed service. We have presence in Europe, in Americas, in Asia. That's the reason why we have storage nodes, multiple storage nodes. I will explain you a little bit more later how does architecture looks like. But before that, I would like to explain you why we choose storage. And there is multiple benefits. I will share a little bit more information about pricing part because I'm, as a head of product, of course, thinking how to make the service commercially viable. And first of all, when we did investigation, what price should be from Chinstack as a commercial entity to our users and customers for the access to a decentralized storage network, and we did a competitive analysis, and of course, you know that Infura, Pinata, Flick, Firebase provide for IPFS access to your files, and they have their own pricing. So we find the most lucrative pricing for our customers. This should be for storing data and, of course, for bandwidth when you upload and download your data. And we found that for storing data, it should be $0.07 for 1 GB per month, and for uploading and downloading data, it should be $0.05 per GB per month. This is most affordable, most cost-efficient price across all competitors. When we find end user price for our customers, we start looking, okay, what solution we can use to actually be still commercially viable and have some margin on top of that. And we did investigation on multiple solutions, of course, starting from centralized storage service like Amazon Web Services or DigitalOcean or OVH, European cloud provider, to find out how much we should pay for the service in case if we still would like to have free replicas, of course, of our files, not just a single replica, and to store a file, to upload, download those files. We did simulation for multiple user scenarios and use cases. And we find out that in case if we will use centralized storage solution, we basically can't make money out of the services. And we start looking on some other solution Storage and different decentralized storage solutions like RViv, Swarm, and such. And we find out that Storage is actually the most cost-efficient, affordable service that we can make business on. And only after that, when we made commercial decision, we start looking how technically do integration of Storage. And as you can see, Storage is sweet spot for any use case that you can use for your decentralized storage solution. That's the reason why we use Storage at first. But of course, there is multiple other benefits Storage is geo-distributed. They always store free replicas. And this is the reason why your data should not be lost. And of course, it's encrypted by default. So how does architecture of Storage and Chinstack service looks like? So of course, we have a user interface and public API to actually expose something to our customers, to our users. And when user upload or just do manipulation with some files or Chinstack service, first of all, there is an engine server with authorization to make sure that exactly this user or customer should have access to this file. And we do authorization with our core backend. And after that, we provide our own implementation of IPFS API. And first of all, what we're doing, we store file that's been uploaded from user in local fast S3 storage in order to have as low latency as possible, as much bandwidth speed while uploading your file. So first of all, we store this file on local hot S3 storage. Then we have a set of IPFS workers who actually put this file from S3 storage to IPFS node, which has a plugin for storage backend. And this IPFS node slowly or maybe not so slowly uploading this file to storage backend network, having free replicas and so on. When we did such experiments, we find out that it could take some time, and definitely this is not something that users should be experienced like in web browser or like using IPFS API over some Linux machine. And definitely having temporary storage with S3 access is something that's drastically increase user experience and reducing latency. And after that, when we put file to storage network, we make sure, okay, this is like uploaded, IPFS worker did the job, and finally, we make sure that this file could be pinned and stored for a long time. And when user accessing this file, like for downloading, we of course have storage network at backend, and we'll like downloading this file from storage network. But we also use hot cache storage on IPFS node when user accessing file very often, like we can give this file to user not from storage network but from local storage for much faster access. This is how we did architecture. It works well. We tested in multiple scenarios, and latency is so good. So we really happy that we did such integration. That's overall architecture. Of course, there is multiple other technical challenges that I definitely would like to discuss with you in case if you have some questions, and we can discuss it later in those rooms that we have here. So basically, that's the main part. However, I have really generous offer and proposal for all of you. Any IPFS Connect participants who have presence here can get access to ChainStack platform and services and get a grant for $1,000 to consume inside ChainStack console for multiple services. Of course, for IPFS API access, but besides IPFS API, as I said, like you can use those grant to get access to RPC endpoints for Ethereum, Polygon, Avalanche, Aptos, Solana, like you name it, any different networks, and with, to have access to our NFT API, subgraphs API, or anything else. So please just scan this QR code, and behind this QR code you will find a link which will go you to ChainStack console with that promo code that you will find on the screen. That's the main part, and my final word to expand your mind while you're building your Web3 products is the following. True and false, soft and hard, upgrade and restart, bootstrap and setup. This is Touchstone where the future is shown. Lumos. Thank you guys. In case if you have some questions, I have a couple of minutes.
Actually, if you can just walk me through the data, we'll do the put, get all the way through. So when I upload a file, it's going to hit your infra in a colo on some type of what, NFS mount? You said it was like being cached, and it's not using IPFS or storage. So you have a file system there, and then you have something running, correct? That.
Yeah. So yes, we. First of all, when we did experiment how it will work, we use multiple scenarios. Okay, let's put file immediately to storage network. Okay, let's put file to some S3 temporary storage. Okay, let's put file to some other distributed network file system. And we did different experiments. We find out that the best user experience we could have in case if we will use local nodes to actually get this file from the user as soon as possible with local NVMe drives in different data centers, like depending on where user is located. So we get this file from user, we store to local hot storage, and we have our backend with the IPFS, so-called IPFS worker that just pulls this data from our local storage to storage network or over IPFS node. And we found that it takes some time. There could be some, retransmit, some errors, lost connection, and it takes some time, but we make sure that this file is being uploaded to storage network, so we can double check that. We can try to fetch this file from storage network from other nodes, from different continents, to make sure that this is accessible. And then we can remove this file from local hot storage and just kept it on storage network. But when user downloading this file from basically chain stack through IPFS API with storage backend, we first of all check, okay, maybe that file has been downloaded recently, and then we doing some caching for this file because we already got this file from storage network and put on local drive and got access to this file to a user. In case if it's not, okay, we download this file from storage network. It usually takes a little bit longer time than having this file on local drive, but it's much faster than when you upload file to storage network, because when you're uploading, it's like has additional encryption, making additional replicas to make sure that this file is actually stored on the network. But when you download file, it becomes much faster than uploading.
And where are the encryption keys held? So there's 2 encryption pathways. I mean, the file comes into your network. I apologize. I have not seen your front end or anything, so we'll have to look at it. But you're encrypting it one time before it hits IPFS, and then you're encrypting it again on storage A?
Yeah. Definitely. So you're right. That's when we go
These
this
are,
file.
really quickly, these are public IPFS nodes, correct, that you're running?
No, this is not public IPFS.
These are private
nodes.
IPFS
This is
nodes.
private IPFS nodes.
Okay.
Yeah. Sorry, we have no time, but I see this on the screen. I definitely would like to speak with you right now in the room. Thank you.
USB-C, or I do have HDMI.
Oh yeah, of course. Yeah, good one.
Yeah, right here. I don't know if I'll have time for questions.
No,
but
sometimes people just yell out the question.
yeah, I'll just ignore them. You can talk to me after if you have questions. Got a lot of content to cover. Let me, gotta pull up the displays real quick, sorry. Yeah, trying to do, there we go. And I need this one on the other screen.
The display, because this will be your main display.
Okay.
So you see it.
Hang on. Cool. All right, sorry about that. This is a lightning talk and I'm moving snail speed. Thanks everyone for coming out here to talk to you about the state of the JavaScript implementation of IPFS, Helia. Yeah, I've got a lot of content to cover, so I'm gonna try to move fast. Here's the agenda, you know, the items are there. So still moving quick, but that's the gist. I'm Russell, I'm gonna put on my Helia swag. So we got some beanies. Yeah, so I'm a senior software engineer at Protocol Labs, working on JavaScript, TypeScript stuff. Yeah, Protocol Labs, IPFS Shipyard. Yeah, that's it. First, we're going to talk about the benefits of Helia, and here's the overview of the benefits I'm going to cover. If you have used JS IPFS or you're still using JS IPFS, The first two are the main reasons that you should switch, but there's lots of reasons. JS IPFS was tightly coupled to Go IPFS. If you haven't heard this, we've been talking about it quite a bit. Helia is not. Helia can pivot, extend, and otherwise improve without being blocked by a sister implementation. And the code and usability with Helia are focused on the needs of JavaScript and TypeScript developers. So instead of ensuring a public API matches another IPFS implementation, we're making sure it works for JavaScript and TypeScript developers. Like that's our primary focus, that it works for the ecosystem that it lives in. Oh, sorry about that. Now, Helia is lean, modular, web native. It's mostly just an orchestrator, and I've got a diagram here on this side. Sorry for kind of flip-flopping. But it's mostly just an orchestrator between the block store, which is where your IPFS content is stored, your content addressable data, and libp2p. The networking and operations is handled by JS libp2p. But all the IPFS functionality mostly lives in the modules that you see here. So Helia UnixFS, Helia strings, DAG.json, et cetera. And Helia, in this code snippet, you can see that you construct a Helia instance and then you pass that to the module. Each of the modules, the pattern here for devs is that it's just an object that contains the first level properties of the Helia instance, which are block store, data store, libp2p, and I think that's it. But yeah, so the module, even without constructing a Helia instance, you can pass it just a block store and an object literal if you need, like we had in Slack, somebody asking about doing completely offline IPFS stuff. So if you don't want to do anything else, you just want to get a CID for some content, you want to see what that looks like, or you already have content that you want to load in a completely offline application for whatever means, you can do that. Here's the diagram. We did just add, Will Scott was talking about the trustless gateways, so we do support that in Helia. You can kind of see we have the block store, which we've then put an abstraction on top of with block brokers. So, the bit swap was already there previously, which then reaches out to the network. And now next to bit swap, we have trustless gateways, and we have this abstraction layer block brokers, which, you can bring your own custom block broker that talks directly to storage or Google Drive or anything really. You can do whatever you want there. It kind of follows, it's a very basic API, but talk to me if you want to learn more about that. Helia is very good at retrieving content. We do implement the latest IPFS specs. So fetching or content retrieval in the IPFS world happens within the Helia networked block store, from this diagram here, that block store. So when you do pass the modules, your Helia instance, UnixFS, or DAG.json module, all of those modules or your custom module that you bring or custom codec, whatever module you add, would benefit from that same content retrieval logic. Helia, it says I have 48 slides. That's not correct. I think some are hidden. Sorry, I got scared for a second. Helia provides all the benefits that you get from using JS libp2p. And as a counterpoint, any drawbacks or functionality that's missing in JS libp2p or problems that you may have if you follow the universal connectivity stuff, there are some, which I'll kind of get into a little bit, but that's the same that we're going to have with Helia if there's any gaps there. So we do have some barriers to adoption, and I'll talk about those, but many are not blockers for most cases, and if you work with us, we can help you get past these issues. So the top two are the main things I was referencing when talking about some gaps with JS libp2p, which are not necessarily due to lack of features in JS libp2p, but the top one, Node.js doesn't support Quick. There's a PR open for that right now that many people have touched. It's been open for 2 years or something. Matt from Matt from Lodestar, I believe, is working on that. I don't know his alias, but sure you can reach out to them or ping We Meet Again or Aching Brain to get in touch with them or me. But yeah, it's a huge PR. It's like, I heard 25,000 lines of code. I haven't dove into it myself. I think it's been broken up a bit, but there's that. And then Kubo and Go libp2p support WebRTC as of 0.24. So that's fantastic, but we still have work to do to enable better browser support in the IPFS network. And then, yeah, that's the browser transport support story. And then also there is a Chromium bug which makes using web transport in the browser pretty difficult. There's some details in that bug, so yeah, you can go there. I've got a very long slide on the next slide coming up where we'll kind of do something with that. But there's only 5 stars on it currently. And then for CommonJS, a lot of the packages, the JavaScript and TypeScript that we've been putting out are ESM only now. So if you're using CommonJS and you can't update, there is an example out there that you can follow to be able to do that. Like it's completely possible. You'll get like a ERR unsupported ESM something error, but like you can get around that if you can't update dynamic import. Yeah, so I'm gonna say it again. There are only 5 stars on that Chromium bug, and this is a lightning talk, but I'm not moving until I see some phones out. So let's get some likes on here. I'm serious. I won't. I'll stay here for the next 7 minutes. If you want IPFS to work in the browser and have like useful nodes in the browser, we need people's support. So please go star that issue. Yeah. Thank you. Sorry for the, you gotta do what you gotta do. I believe in the system, so let's make it work. And then those were kind of high level issues. So these are some things that I've seen from individuals on the Discuss forums, which I'll have links to in a later slide and things like that. But I created, there are common complaints coming from the other higher level issues I just mentioned. For the network one at the bottom, Helia uses, like it didn't use libp2p defaults at first when it was first created, and you had to like construct libp2p yourself. Right now, it does come with sane defaults, but if connectivity, networking isn't working like you like you want it to, if it's not doing something, that all of that is handled by JS libp2p, and like you can reach out to us, talk to others to find out like what you may need to do. But it's really good that we're kind of informing developers and consumers of Helia more about JS libp2p instead of hiding it all away like it was done with JS IPFS. A quick call out. For production use cases, you do want to use a non-memory based data store and block store with Helia. By default, it uses in-memory. And if you're walking the DHT, which is enabled by default, and you're building up your peer store and you have we have 20,000 IPFS nodes or something. If you end up storing all of those in an in-memory data store, then that is going to crash your tab. That is going to, I just ran into, look like a memory leak. I forgot, it's an in-memory store with Helia HTTP Gateway, which I'll kind of reference a little bit. So what's next for Helia? Our website currently points to auto-generated API documentation right now, but we will update that. That's helia.io, here on the bomb sweater. Gateways will be using Helia in a service worker soon. Like that's something I'm very passionate about, and some of the leadership is here, so maybe they don't know that, but it's going to happen. Yeah, you should use Helia too. Like you should be fetching content directly using Helia. You can do that from your web app. You don't need to point people to IPFS.io. Don't use source IPFS.io for your images or whatever. Just you can fetch that via Helia, like with a service worker on your web app. All of your users are then, you're not bombarding the infrastructure that we host for free with those requests, and then your users should ideally be getting that faster overall. Direct browser to browser is possible today. It does work today, but it will be easier as web transport and WebRTC become more available on the network. And then browser authored content, like we're going to solve that, and we will sunset those preload nodes that you use with JS IPFS, and that's why JS IPFS can actually like serve content from the browser. It's not actually doing that. But yeah, we're gonna solve that in the real P2P way. And that's gonna be amazing. As a TypeScript and JavaScript engineer, these items are really exciting to me. If they excite you as well, let us know. And maybe we can work on them together. Maybe you can like build that and we will use that, point everybody to your thing. Like that's great. We want that from the community. But yeah, if any of these excite you, there are some work that have gone into some of these. I've got links to the GitHub issues, so go there, extend them, comment on them, open issues, whatever. But yeah, just get involved. And speaking of getting involved, now what? Like how do you get involved? If you're an IPFS or a Amino DHT node operator, enable browser compatible transports. Stop disabling web transport. If you have to disable web transport because it doesn't work for your server farm or your instance for whatever reason, which implementation are you on? Can you reach out to the maintainers of that implementation and see if we can work through those issues with you? Like reach out. We're here to help. Web application devs and library authors, contribute, get involved, give us feedback. Like if you've tried using Helia and it hasn't worked, why hasn't it worked? Have you opened an issue? Is there an existing issue? It's probably browser authored content, golden path issues that we're familiar with. Yeah, let us know. If there is not an issue, reach out. We're very friendly, pretty cool. I mean, if you haven't seen my hoodie and everything, like we're pretty cool. For protocol engineers, like come contribute directly to Helia and JS libp2p or get involved in the IPFS specs. There's a link for that there. There's, we're moving forward. There is a spec open, which I'll link to, I think in the later slide, for writable IPFS nodes, basically, like putting to any node instead of like the pinning API or something. For web platform folks, I see you, Dietrich. Let's push on W3C, IETF, Node.js, Chromium teams to support all of these things that will make P2P work everywhere. Let's make it happen. If you're just, following and you're curious, you're interested in IPFS, follow along. Say like, hey, what this guy said was very cool. I think we should do that. Like that's useful feedback and information. So where are the links, Abe? Right here. Yeah, there's, our website, helia.io. I got 1 minute left. I made it. This is awesome. I thought I was going to take 20 minutes. GitHub repo, wiki, and our wiki has recordings and presentations, which this one will be posted to after this. I actually have an old one I need to post there. We have a working group that meets every Thursday. There is one scheduled for tonight, which I haven't canceled, and I'm still debating whether I am going to host that one. Probably will. So it would be really cool if I could host that here. I don't know if that'll work, but yeah, it'd be cool. It's like 6 p.m., 7 p.m. tonight. Yeah, all those links. So I'm gonna try to pronounce this. I wrote my own wording for it. Çok teşekkür ederim. Thank you. Huge shout out to Aching Brain, Mass Chad, We Meet Again, and WizKid. If you have questions, just find me somewhere. Cool.
Sweet. Hey, Des.
Yeah, here to talk about Indexing Co., company I'm running, and our road to what we're calling Data 3.0. Try to move kind of fast, just for the sake of time here. Shortly about me, it's kind of a Web 2 life, Web 3 life. Started out, got a math degree, easiest way out of college. Moved into software, realized I could make money writing code. It was great, traveled, did the thing. Ended up in startups, a lot of time spent building SaaS products, SaaS companies. 2017, got into Web3. So I met my now co-founder building Imbrex. We were trying to do real estate on-chain. Way too early to get a real estate agent to install MetaMask. A lot of issues there, but we were using IPFS way back then. So I had a lot of fun, been in the community. Then went on to Coinbase, spent a year and a half kind of working on some of the internal tooling and data platform tools there. And coming out of that, now founded the indexing company. I'll dive into that in a sec. So really what we're solving is trying to empower other people, other companies to build Web3 products. And so today, if you go and try to build something, you're dealing with decentralized data. You're probably trying to build some sort of decentralized app. There's no decentralized connective tissue. So the data is decentralized, your app's decentralized, your users are decentralized, but actually trying to use all that data ends up being a centralization problem. So really what ends up happening is everybody is reinventing the wheel on this infrastructure. Building in-house is hard, even if you're using something like the Graph or another API provider. You're taking that data, you're reprocessing it, you're throwing it in a database, and yeah, you end up with solutions like this. It's painful, it's expensive, it's not great. So the way we kind of think about this is a Web3 data trilemma. So we have the speed that you can access the data. So this is the full round trip. Once it's on chain, how fast can you make that usable for your users? The breadth of the data, so if you're dealing with multi-chain, off-chain, what is the full scope of data that you need? And then also the depth. And this is really about tailoring that data to meet your users and your product's use cases. Yeah, I don't think there's a one-size-fits-all solution here by any means. I think there's great companies doing different focused pieces here. That's kind of the scope of the problem space that we're working in. So a little bit about indexing for anybody that doesn't know already. It's kind of a 101. The classic versions, you have search engines. So this is your Googles. They're crawling the internet. They're taking all that data, making it searchable, right? Another common version is databases. You have things like hash tables where you can quickly look up information, query it more readily. Really all this started with index cards at libraries, in my opinion. So you had librarians going out, figuring out the books and making that more readily accessible. Kind of see a theme here. Indexing is really about taking data, information, whatever it is, and making it more readily usable. It's really that utility that we're getting at. So now looking at the space of indexing in Web3, this is kind of just a really simplistic view of what indexing means here. So at the bottom of this diagram, you have a UI, a browser, a user, somebody doing an action. Those actions usually end up as transactions on chain somewhere. You then have infrastructure, and I just put that in quotes for a moment, but that infrastructure is pulling that data back off chain, probably putting it in a database somewhere, and that database is served back to your users. So you kind of get this cyclical nature going. And so diving a little bit deeper on the infrastructure. This is really the core of what's difficult. Usually this involves some sort of queues, you're dealing with multiple services, maybe you've got a microservice architecture, maybe there's a caching layer, maybe you have a CDN, maybe you have multiple databases, you probably have monitoring in place. Dealing with the RPC providers, orchestration, queues, monitoring, aggregations, the list goes on and on. The point is, it's really difficult, and all of this is in-house. So it's centralized, it's difficult, it's expensive, you get the theme. Surprise, indexing code does indexing. So we're trying to empower other Web3 companies to build their products, make that data more usable. And one of the ways that we're doing this is we're approaching all of indexing as an infrastructure problem instead of a data problem. So we're really trying to think of ways to rebuild indexing infrastructure, what we were highlighting earlier, from the ground up to be fully distributed. And so you'll see here, kind of using the Ethereum Lodo as a drop-in for any blockchain. We're taking data from a blockchain, caching it into blob storage, queuing up distributed jobs, and then we have a whole pool of nodes that go and operate on those jobs. So we're able to run thousands of nodes at once. This lets us get really good performance, really good throughput. We can do things like index all of Ethereum in about an hour. Yeah, this is kind of where we're at. You'll see here, though, notably, there's still two major centralized pieces. The in-database is centralized, and the queue architecture is centralized. So we'll get into that in a sec. So hurdles we faced along the way, because we're trying to do distributed computing, that comes with its own flavors of issues. Notably, what I was touching on just previously is our queuing architecture can't quite handle the throughput we're getting. So we've tried the Kafkas, we've tried the pub subs, but as you start getting into, say, billions of jobs per day, those solutions tend to fall apart a little bit. So we're trying to think through ways to make that more distributed instead of having centralized bottlenecks. And then the other big one is the databases that we end up writing to. So a lot of what we do is we take the data off chain, we perform some business logic on it, we process it. That ends up in somebody else's database. Those databases themselves are centralized by design, and so those have their own throughput limitations. So what we're really trying to do is imagine what if. So what if we could have a fully decentralized data infrastructure? And this is what we mean by data 3.0. The data started decentralized, let's process it in a decentralized way and make it accessible in a decentralized way. So it's processed and accessed exactly where it's needed. So this is kind of roughly how we're envisioning tomorrow's architecture. This is where you've got mobile devices, computers, individual humans accessing the data they need from the apps that they're using, and those apps and those humans and those devices are also doing the work of indexing that data in the first place. So they're taking the data from a decentralized source, i.e. a blockchain, processing that data, putting it back out into some sort of decentralized composable data layer, and then able to query that directly. So you remove all the centralized authorities, you remove the centralized bottlenecks, and you kind of end up with this peer-to-peer network, if you will. Yeah, and so we're kind of at this fun inflection point, in my opinion, where innovations like what we're hearing today here at IPFS are making not just the infrastructure possible for things like this, but the data can now be transformed. There can be new innovations there. So getting into IPFS and how this plays in. I mentioned earlier, back in the early days of Imbrex 2017, we were playing with IPFS, OrbitDB, doing some pseudo peer-to-peer queues, if you will. We were also doing distributed signing of documents. So if you wanted to buy a house, we let you sign the document. It was encrypted, went on IPFS. Lots of fun stuff there. We're trying to bring some of those concepts back into indexing code now. So we talked a little bit about how queuing architecture isn't holding up at scale. So we're starting to experiment with, well, what if we could do queues on IPFS itself and do those localized? So you might have a localized set of nodes that are really interested in Ethereum data. Another that's interested in NFTs on Base or Frentech or whatever it is. Those nodes don't have to be geographically centralized, but as long as they're interested in the same topics, it gives us a way to potentially scale this out horizontally using things like IPFS. And so that's what we're starting to explore. And really, all this is possible because, as we all know now, IPFS, the content is data addressed, which means it's available anywhere, anytime, and without a centralized authority. Yeah, we're really trying to get to interplanetary data. I think it's always been IPFS is kind of the joke here. The simplified architecture here, taking our vision for tomorrow, you throw an IPFS node on top of it, and you'd get this way for everybody to interact in this broader network. And yeah, can't do this alone. I don't think we're going to come up with a holistic solution at the end. Anybody building anything, please reach out. Yeah, my information's here. Yeah, would love to chat. Yeah. Thank you. Yeah, if there's any questions. Cool.
Okay, great. Thank you very much.
Of course. I'll share.
Hi, I'm Alan, and that's me on the screen. I work at Daghouse. I'm a software developer, software engineer, building Web3.storage. It's this nice thing. So I'd like to start with what Web3.storage is. It's the easiest way to onboard data to the decentralized web, and that means IPFS and Filecoin. And this looks like a serious talk from that slide, but it is in fact not. Half of these things on the screen right now don't exist, but they're kind of cool. I'm going to tell you what I mean by them, but they kind of relate to cool features of Web3.storage that I'm interested to talk about. So let's do it. So I'm going to start with the past and move into the future from there, I guess. So 2021, that's where it all began. Web3.storage spun out of a project that was called NFT.storage. And it was kind of like this, this amazing thing that happened. We built NFT.storage really quickly, and it was for just helping onboard data into Filecoin. But people started using it loads, and you can see from the testimonials that people were kind of jazzed about it, and so it kind of took off. It got big, and then weird things happened, like other people started talking about it that I don't even know, and then there's like swag and stuff that happened, including like bum bags, or what do you call? I don't know. Anyway, and then like whole buildings get branded as NFT storage, and then stuff like this happens, and and I was sat there sort of just typing away, thinking like, what is going on? And then like NFT storage is in the airport, and then whole trains are branded NFT storage. And then this guy on the internet sings a song about NFT storage. What the heck? What is going on? So that was 2021, a bit of a wild time. And so basically NFT storage was built in 2 weeks. It was a tool to be used by an NFT hackathon. And the idea was it would just allow them to store NFTs on IPFS and Filecoin. Filecoin had just launched at the time, and it was looking to onboard data quickly and also fix the bugs. It wasn't always easy to onboard or offboard data onto Filecoin at that time. So anyway, enough about NFT.storage. This is the first iteration of Web3.storage, which kind of came about as like you know what, we've got this cool NFT storage thing for NFTs, but what if there was more, like a more generic kind of for every type of data solution? And so Web3.storage came about. The big thing about Web3.storage was that it was a major step towards Web3 from NFT storage, which was very kind of Web 2 oriented sort of service. And instead of uploading files directly to the service, we content addressed them on the client side. And we started accepting car files. So when you import stuff into IPFS, it becomes a DAG, it has a CID, and if you want to send that DAG somewhere, then typically you'd kind of pack it up into a car file. And so cars were our primary upload means at that time. And our architecture at the time was like, I mean, it says Fauna there, but we moved from Fauna to a big, giant Postgres. We were using IPFS cluster at the time, and Cloudflare workers to accept uploads. So that's kind of fun. Cool. And then we kind of got into this, what I'm calling the steady state, except actually, it wasn't very steady. We had rainbow graphs. Rainbow graphs look nice. They are not nice. Ideally, you want your graphs to be high or low, depending on if you want things to be high or low. You don't want them to be jazzing around everywhere. So rainbow graphs like this make for good screensavers, but actually our service was struggling. Our IPFS cluster instance grew to over 50 nodes. And what we were finding, as you see in the top left there, is that any given node in the cluster was receiving a lot of writes because there were write targets, but there were also read targets as well. And also because of DHT stuff that needs to happen, they were re-providing to the DHT, and sometimes they had, well, we had to learn this, but don't let your IPFS nodes get too big, too full of data, because at some point, the list of things that it needs to send to the DHT to keep saying that I have this thing gets too big, and they sort of expire before they get to the front of the queue, and there's just too many things to get through, and the node basically gets super busy. A lot of our nodes were like that hot, tired face there. So anyway, that was those times. And then, so the steady state came around when Elastic IPFS came around. It really saved us from that. Elastic IPFS is a cloud-native IPFS implementation, and the basis of it is separating those read and write pipelines to achieve a much larger scale. And it also leans into car files at rest. So what we did was we started to write car files to buckets and just make a big index of like the block indexes within cars. And then our bitswap implementation in Elastic IPFS just reads, it uses HTTP range requests to read specific blocks out of cars. And you can do kind of fun stuff with that. Like if you've got two blocks that are close together, you can make one request with both blocks in it and stuff like that. So that's cool. And so with Elastic IPFS, we were eventually able to retire our IPFS cluster. I said it was like over 50 nodes at the end of it, but that saved us many thousands of dollars every month, which was rad. It's not to say that IPFS cluster isn't any good or at scale. We had tremendous scale with IPFS cluster, but we needed to move on from there at a certain point. And then this thing called Freeway came along, and Freeway was a kind of speed optimization and cost-saving exercise. So Freeway is kind of a no database IPFS gateway where Elastic IPFS has a database which stores like the block offsets in a database. Freeway, the idea was like we index the car, but we store the index as a file. The index is just a carv2 file, carv2 index file. And we read from that index, and we have symlinks set up as well, which sort of say this interesting CID, like a root of a file or root of a whole DAG, is in these car files, so you can fetch it out of there. So you can read the index and then get the blocks out. So Freeway basically just serves data directly from car files at rest, rather than going over bitswap, and that's kind of faster and saved us a lot of egress from bitswap. Cool, okay, so we spent almost all my time on the past. So anyway, things were better now. The fires were less, and we still had some centralized infra, though. We had centralized upload targets. We would be accepting data through Cloudflare workers. You could only send it to us. We had an opaque data aggregation pipeline. Like you would send us stuff, and at some point in the future, it would become aggregated together into a bigger chunk of data that would go into a Filecoin deal, and at some point in the future, you'd get a Filecoin deal, but you had no idea like what was happening between the point you sent it to us and that. We also had unverifiable operations, so you literally just sent us stuff. There was no proof of who had stored what, aside from our giant Postgres, which you could look at, and I guess, but big giant Postgres is probably not what we want, at least for this crowd. And so, yeah, we weren't able to take advantage of content addressing. The beauty of content addressing is that if you're content addressing, you actually don't need to send the data if someone's already got that hash. And so what we had to do is that you would always have to send a car to us. You just always had to do that. And so that's not good. So we're leaning into UCANs to solve a lot of these problems. UCANs are user-controlled authorization networks, and they use public key cryptography. So you sign a UCAN, and they have this concept of capabilities and delegations, which is really cool. So some examples of capabilities that we, or abilities that we have in our system, are StoreAdd for storing some data. You can offer a piece to Filecoin for aggregation and deals, and you can list uploads and stuff like that. So anyway, you can delegate those capabilities to other people, and they can delegate on to other people as well. And in a UCAN, the delegation chain is included. So every UCAN that gets sent around has this full chain of authority like baked in, which is great. So there's no like central authorization server. There doesn't need to be because of the delegation chain that's baked into UCANs. But there is now verifiability for operations, so you can see when you've been when you've sent something and who's done what. And so this is kind of what I mean by that title of the talk, which is Zero Knowledge Auth. You don't need to have any knowledge of of the authorization list or whatever, because it's all baked into the UCAN, and that's kind of what they provide, which is really interesting, I think. So basically, it's all cute Disney characters in this new version. We built this UCAN RPC library called UCanto, and that allows you to make invocations with UCAN. So it's a way of using those capabilities you've been delegated to get tasks done. And then you get receipts from those UCAN invocations, and they communicate the results from tasks. And the receipts kind of can look a little bit like this. There's more to them than this, but I've super simplified it. But basically, it's a result or a CID of a task that will complete in the future, and you can check in on that task at a later date and see if it has happened. And so we have this data aggregation pipeline. You can kind of see how if we've sent a signed UCAN to say invocation to say I want to store this or put this piece in Filecoin, and we might get a future task that's like it's going to be aggregated. Check that later, and then you could check in on that and get a receipt for the aggregation, so you can see which bigger aggregate piece your piece has been aggregated in, and that will include like an inclusion proof, so you can pick out the exact thing that you're storing. But you can follow it through all the way. So once you've got that aggregate, you would then get a future task, which is like this is going to make it into a Filecoin deal, and you can check in on that with the aggregate and receive the deal information. So what is called like a data aggregation proof, where you have like the deal ID plus the inclusion proof for your piece within the bigger piece. So yeah, it's rad because we've now got this amazingly verifiable system that you can follow through that we just never had before. So that's really fun. And also thanks to the UCAN receipts is that we now have these I guess capability of being able to have decentralized upload targets. So yeah, what you do with a store add invocation in our system is you say, I'd like to store this car file, and with car files we actually content address them as well, so they get their own CID. So you say, I want to store this CID, this car file, on Filecoin, on hot storage, wherever, and you get back a receipt that says, okay, this is where you put it, and so that URL is currently like just a bucket that you can put stuff to, but in the future that could be some other target. That could be like a Saturn node, for example, or it could be a storage provider themselves. We also spec out all of our UCAN systems, so there's this hope that people could implement some of the spec and become targets for for posting aggregates to. They could aggregate data together, or they could receive aggregates for putting in deals. But and so with the decentralized upload targets, this gives us an opportunity to say, we've already got this car, it's already in a deal. Like, you don't need to send this to us. So when you do a store add, you get back a really quick response that says, that is done, you don't need to do anything. And this is from the talk title again, what I call infinite compression. Is not really that, but in all seriousness, content addressing is rad, right? Imagine just being able to do that. And if you want to resume, if you've got a big video, say, and what we do is we shard it up into many car files, you could go through, you could get halfway through and resume, and basically, if you want to resume, you'll get like a bunch of things saying, we've got these cars, and you can then continue where you were left off, because maybe you got on an airplane or your internet dropped out or whatever. So yeah, very cool. And so we launched the UCAN offering of Web3.storage literally a couple of days ago. So all of these benefits have just been realized. Now, the future is unwritten. That's why this slide is relatively blank. And also, I didn't have much time. So, but what we would like to do in the future is we'd actually like to decentralize that upload target. We'd like to maybe put it in like hot storage for Saturn, perhaps. I don't know exactly how it would work, but that's the idea. We've got that opportunity now. We also run our own gateways. We'd love to sort of offload some of that responsibility onto Saturn, so it would be cool to work with them to realize that opportunity. And there's a whole bunch of other stuff, like we store some metadata in the database. It would be really nice if actually all user data was just a DAG that they stored in their space, including like all of the indexes and things that we do. Yeah, there's this other awesome thing where we'd love to do like what we call dilution pricing, which is like if you're storing something and someone else is storing something as well, then maybe you halve the cost of storing it, and like the more people, the less you pay, because it's not actually costing us any more money to store. So anyway, the future is unwritten, and I am over time by 2 minutes, but I'm Alan. I've been working at DAG House for a long time now. We are having fun and making awesome things. Web3.storage is good fun. You should check it out because it has changed significantly into this awesome new system now, and I'm really proud of it. So come talk to me after if you want to talk about that sort of thing. Come to the workshop later where you can, oh yeah, the workshop, right? You can actually use it. There's a workshop later at 4. It's billed as like a joint Saturn Web3 storage workshop, and you can actually use the upload service at the workshop, and it's guaranteed fun. So that's our house in the Merkel Forest. Thank you very much.
I need a dongle.
This is for the clicker.
This is dongle. Dongle.
Ah, okay. Everybody else had like HDMI.
Yeah, I'm a CEO, so I have the baby computer that doesn't have that.
Just learn me how to do that, so I guess I'll find. Okay, just a moment. Yeah, we need to mirror the display.
It is mirrored.
It is mirrored.
Oh, no, hang on. Yeah, it's mirrored. Like me to unmirror and mirror again?
Click, an extra click. Thank you.
Hello. I know I'm between you and lunch, and some of you have seen this before, but this is was supposed to be Brooklyn Zelenka, so you get the slightly more high-level version from me, Boris Mann, founder and CEO of Fission. So what Fission does is we are a protocol-first applied research and implementation team. As you've heard from some other talks, we've been doing a lot of work doing protocol-first development and working with lots of great partners like Web3 storage in designing these systems so that they can be used for all sorts of things, but then interoperate. So we're well known for the protocols that we've been working on over the last couple of years. An edge computing stack with cute characters, the UCAN, Toucan, Winnie, the WinFS cat, our encrypted file system, and this talk is about IPVM, and that's the Homestar Toucan. Please don't ask why the star is upside down. We've been really happy to see the widespread adoption of UCAN and WinFS across the PL ecosystem and beyond. We see that protocol layer being a public good. It's the thing that lets us build larger systems that people can go different directions, build apps, build protocols, build commercial services, build open and commons networks, tie into other Web3 ecosystems. IPFS has this unique capability to connect, I know it's the name of the conference, all of Web3 because it's the part at the edge that talks to everybody else and it talks to the user. So the Interplanetary Virtual Machine, or IPVM, a little background from Brooklyn. So to date, IPFS has been a project focused on data. It's a specification for bringing content address execution to content addressed data. To this end, the spec aims to be the easiest, fastest, most secure, and open way to run decentralized compute jobs everywhere. These are the sorts of goals we need to set ourselves. We can't just stop and say, we'll make things slightly better and be centralized. So we always have to be going down this path. And Hannah's talk does an amazing, amazing job of laying the groundwork of why and how this is so super important. So the sort of like more pitchy sort of way, and this is pitching a protocol, not a singular product, is that IPVM should be an open, decentralized, and local first competitor to AWS Lambda. What? How can you just sit there and say that you're going to take on AWS? Aha, because I'm not taking it on by myself. I'm making a protocol that many people can take paths and ideally interoperate and build large open systems together, which can, in aggregate, in fact, be larger than any one of the hypercloud providers. There are many excellent deep dive technical talks that range from half hour to an hour of really dense material by Zishan Lakhani and Brooklyn Zelenka, who have been the main two applied researchers on the project, at github.com/IPVM-WG for working group. And it was co-developed with folks at Bacalhau and the FVM to align on the things that we would need in the future. So check that out. So Homestar is the IPVM implementation that Fission has been working on. We've learned from the IPFS ecosystem and tried to go straight to a protocol-first approach where we have multiple implementations that people can get started with. Fission's focus with Homestar is it's written in Rust and it's focused on WebAssembly functions. As an example, Bacalhau is focused on Docker jobs. It's got a libp2p-based networking layer built in. It works alongside Kubo and other IPFS implementations and creates a network of computation. I literally just added this. Super great that Alan talked about this. So just like Web3 storage, store, add, Homestar computation has receipts. So this is the part where we start understanding, oh, these things fit together, right? Effectively, the Web3 storage system has computation built in. It invokes does a UCAN invocation, and does these little compute jobs specific to their system. And it can compose, so we don't have to be tightly integrated in their system, but you can have a workflow that kicks out and does a Web3 storage job. So in Homestar, in IPVM, the protocol, if a workflow or task is being computed, the receipt has the value that you can just fetch from the network. So gossip subbed over libp2p. So any of these Homestar nodes that are connected together or have the content addresses on some content addressable store, you can check to see if it has already been computed and just fetched it. And that's that UCAN invocation spec. Yes, it's specs all the way up and down. So the Everywhere Computer is Fission's platform to support a protocol. And ultimately, this is the work that the IPFS and Filecoin ecosystem has been doing a flurry of specs, getting them working at all, and then climbing the path towards productization, either inside a team or seeing it spread between other teams taking both open source and commercial approaches to things. So the Everywhere Computer, lots of people have platforms. The Everywhere Computer is Fission's. It's a branded and supported distribution that bundles Homestar, a control panel, a function and workflow marketplace, and managed compute resources. As a developer, you write functions and integrate custom services. As a user, bring your own compute or rent hours. As a computation provider, bring custom resources and register them with the network. And there's lots of interesting stuff. I've already had discussions with someone who's building GPU-heavy compute. And I said, absolutely, we would have a profile for running a Homestar node that would advertise that that node has hefty GPU resources. Some of the IPVM functions running in a low-end Android phone would obviously say like, I don't have a lot of GPU. Can I farm this out to someone who has? And then as an on or off-chain ecosystem, federate your own network with the function, services, and resources that matter to you. So in the Web3 space, there's been a lot of discussion about application-specific blockchains. And we've got roll-ups and layers and all of these other things like that. And those can be very customized. Some of those things are going to run as on-chain smart contracts, which are very expensive and consensus important. And other things you're going to want to have more storage, more massive compute off-chain. So one can imagine applications where you have a set of functions. You know which functions your application needs. They can be broken up into small pieces of computation. You could stake on-chain for those functions. You could make everyone keep them around. You can have a type of IPFS desktop type thing, except it does computation that run backends as a team together. And those are some of the directions we see going with the Everywhere Computer. So we've seen proprietary platforms start with generous freemium plans and then start targeting an enterprise market and really squeeze entry-level plans. So my evil plan is that the great integrated DX of a Vercel, a Netfly, or Heroku in days gone by, all of those systems are platforms that are not open source. They have a number of different capabilities around data, identity, data, and compute. If you outgrow those platforms, you have no choice but to essentially rewrite from scratch. If a developer starts on those systems and then hits up the edges and goes, I can't afford this much, they have no other options. They throw out their entire platform investment. And so that's why it's so important for me to focus on protocols, not just open source cores, but protocols. So imagine each of those things being unbundled. We've got a UCAN layer, we've got a storage layer, we've got a compute layer, a Lambda layer essentially. And so people might start on Everywhere Computer and use some of our managed resources. Oh man, this is getting expensive. Great, spin up your own network of Homestar nodes. And I think this is one of the things that breaks the problem with freemium. Spend that early investor money to pay for a crap ton of resources, and then as that drives up, start putting the prices in and people are locked in. We're not going to do that. The freemium version of this is, go ahead, run a couple of Homestar nodes. And that starts with something as simple as the workshop that you can join us for later today. Will you run a single Homestar node on your own desktop, and it can power the functions that you need it to run. So, and we think that's a really interesting direction for, like I said, like breaking that kind of like freemium trap. There's some future things around compute to earn. Everybody's like, what's your complicated tokenomics? And I'm like, I'm actually just going to do this thing where we're going to charge people for the compute that they use. It's kind of uncontroversial. You pay EC2. As you can see, everywhere, computer is in fact EC1. We know 1 is better than 2, so, you know, obviously. The other part that we have to think about here is we're playing back and forth with this concept of where stuff runs. I mentioned it briefly with the low-end Android phone. So WASM can run in client browsers on desktop and web. Again, if you went to Hannah's talk, there's this dream that in part we're heading towards that is kind of a joke, but not a joke of the Silicon Valley TV show. So with WASM, how do we create frameworks that app developers can use to offload computation to client-owned compute when available? Every client compute cycle we run is one that doesn't need to go to pay server clouds. So how many people in the room are familiar with Figma? A bunch of hands go up. So Figma recently got bought by Adobe. And one of the reasons that Figma is used broadly is it's this kind of multiplayer Photoshop in the cloud. Great for design, buttery smooth, works great. A ton of Figma is powered by WASM, where a lot of that functionality is actually running in your browser. So lots of those things don't need to hit servers that ultimately would need to get paid for by Adobe. And that means also that smaller teams don't need to be Figma or Adobe sized because you're saying, no problem, we're actually just running this client side for lots of those things. We're having discussions with some relatively large players. There are teams at Intel and Google that are interested on standardizing this even more. Played around with some concepts. Maybe it's like decentralized service workers. Once you have this concept of service workers, maybe you don't even actually need to run it in the particular browser that you're on, but you can delegate it off to somewhere else to run and send the results back. If you're interested in this, I'll have links later. Leave a note in the comments. We're likely going to spin up a W3C community group to explore this kind of portable WASM so that people can build WASM-powered apps that automatically have compute that travels to where it needs to be. And again, at scale, you're paying for every single compute cycle to a hosted provider. So at scale, that should be, this approach should save people a lot of money. Some future things. If you're going to do this in a decentralized way, we're going to need payments. Vision's approach is that all of our stuff should work at the edge and it should work in browsers everywhere, and it shouldn't require a blockchain. It can connect to different blockchain ecosystems for incentivization and payment and other things like that. Brooke and the team have done some work around IPFS-based payment channels where you could then settle to fiat or settle to a token of some kind. I know that I've caught up with the FEM team. We keep going back and forth of where we're at. We're writing in Rust. The FEM team is writing in Rust, and have been excited to talk that there's reuse of IPVM components for FEM. Again, they were part of the design process of creating the protocol, so this is not a surprise. It's just that we're coming back around and going like, yes, we're ready for this. I mentioned Kubo earlier. We use that today to bundle it. IRO tastes great with Homestar. Because it's also in Rust, unlike Kubo, we can probably even integrate it directly into Homestar or vice versa. So some of these also become toolkits. If you have interesting ideas of making public, private, or mixed networks, you could combine Homestar and IRO in interesting ways. Integration into ecosystems, app chains, L2s, mainnets. If you are interested in adding edge computation, off-chain computation to your ecosystem, let's talk. We want to empower you to run your own network of Homestars. Further language support. So right now, you can write functions in Rust to WASM. That's a happy path. Ugo and our team has done some great work to make it easy to do JavaScript to WASM. Python is a large community that's likely next and has some good tooling around that. Right after lunch, we have a workshop that will be in Neuchâtel. Please join us. We'll have you install Homestar. Try it for yourself. We'll gossip some receipts on the network. Knock on wood that this all works on this hotel network. And you can go to everywhere.computer and join the early access beta. Give us some info on what you want to do. We want to support you in being successful in doing that. That's the end of the talk. Any quick questions before we break for lunch? Catch me at lunch. Thank you so much.
Hey, hey. Can you... Sound check. Ses deneme 1, 2, 3. Ses deneme. Can you hear my sound stream? No?
Efe sen bunu al, onu bana ver.
It's alright?
Yes, I hear.
Okay.
It's just delayed.
Now kapat abi.
kind of post-lunch, so we're going to get lots more people, or at least some more people trickling in. And I still have people on my list that I'm hoping at the last minute will show up to actually give their lightning talk. So welcome to what we're calling the Boom Sessions. This is sort of like a sub-session within IPFS Connect that is focused on like in-flight exciting things that folks are working on. And by folks, I mean developers, creators, builders, even users that are doing interesting things in the IPFS space that is maybe like not finished yet, or it's still a new idea, or they just want to share their philosophy on how you do things in the IPFS ecosystem. So Boom is a place for that. And you can see the sort of like very generic white slides that we have here, because the idea is you're not necessarily representing your company or your organization or even yourself. You're just representing your ideas. And so we'll try and keep it really informal. We'll try and keep it really quick. We'll try and keep it really fun. And we'll try and keep it somewhat on time. So we got 90 minutes and a bunch of people who want to talk between 5 and 10 minutes. So without much further ado, I'm going to introduce our first speaker, who is Jim from my team, which is me cheating a little bit, but I'll get him up here so that you can see kind of the format that we're looking for, the timing and all that stuff. Jim, you're going to see a countdown in front of you. You got a maximum of 10 minutes, and I'm going to rudely stand up and cut you off at 10 minutes. Okay. So we're going to keep it on time, all right?
So I just talk too fast.
So you got to talk fast. Here we go. All of these talks are recorded, so if it's something that is potentially of interest to your community, you can reference it later, okay? And Jim, take it away.
All right, do I put this just on top of here, yeah?
Yes.
Right. Okay, I guess I'm going. So, I'm here to talk about design, which I know I'm probably one of the only people, if not the only person, talking about design at IPFS Connect, if not the whole thing. Sorry. Sorry. But yeah, but about why you as developers and builders should care about this sort of thing. And yeah, as Carson mentioned, I work at Textile and we're making Tableland. I'm working on this thing called Tableland Studio primarily, which is the UI to build distributed databases and manage them and that sort of thing. So I have a history. So I come from a family of developers. So I like to think that I understand how many of you think and like to work. But I ended up in art school. I have 2 design degrees somehow. But I'm interested in data and how people use it and how it affects our lives. And that kind of brought me into the IPFS community, among other things. And yeah, what do we mean when we say design? This can mean loads of things. People think it means interior design. People think it means graphic design. And it's sort of all of that, really. In this kind of context, we're talking about the design of user experience for software, I guess, and applications, that sort of thing. 2 big ones, user-centered design is, well, you have a user, you should probably make something they want to use. That's the gist of it. And then design thinking is a more popular term lately, which basically means that you kind of just have loops of working and testing and prototyping and that sort of thing. And kind of what it boils down to is just a creative solution to a problem. And I guess what does creative mean? It can mean, people think that it comes from space, that artists and designers get this, they have this sort of, intuition, really. And that's not necessarily the case because everybody has intuition, And when you're coming up with creative solutions to problems, you should have some sort of evidence with that. So you should have you have facts, things that you can kind of point to. And then finally, you should have experience, meaning learning. You've figured things out over time. Things have been tested. And so that's all fine and dandy, right? To have these kind of high-floating ideas about, wow, we're going to be really creative with solutions to dev tools and that. But what's some way we can think about that? And this is probably one of the better ones, right? And this could be similar to many development cycles. And it's a way to just kind of break things up. And I guess the front end of that empathizing, defining, and ideating. Well, actually, all of it's super important, basically. But this is just one way to think about it, really. And another way to think about it is this thing called the double diamond. And this came out, the UK Design Council came up with this. And this is just another really framework to kind of how can we come up with ideas? How can we kind of figure out what the problems really are, which is the main gist of all this? How can we talk to real, actual people and users? And kind of how can we come up with some solutions and then validate those solutions. And that's kind of what it all boils down to. Now, and this is kind of how this applies to dev tools, really. And it's because that it's particularly suited for these ill-defined or unknown problems. And that's because the design is often missing this far up the stack. And the problem with that is that all of you are building tools for other people building tools, generally, right? That there's these like kind of cascading levels of tool building. And the further down or up, I guess you could say, that you go in that stack, you know less and less of what's actually being done. And that's extremely problematic. So you have to begin to think about kind of these knock-on effects. And hopefully, design thinking and this idea of ideating and refining and whatnot is some way to help frame this. And yeah, you have to think about what people are building. And the other thing that so again, like I said, my dad was a programmer in the 60s, and my sister, my brother, et cetera, et cetera. And then there's this thing, and all of my friends are programmers, but it's this idea that the programmer, although you are a developer, the way that somebody else is developing is not necessarily the same. In fact, it's probably different. So yeah, here's some ways to potentially think about this sort of thing. So kind of at a cursory level is, yeah, shifting problem spaces. Because you're making tools, you don't know how people are going to use those necessarily. You can kind of have some vague idea, but you have to think about not just your users, who are also building tools, but your users' users. So where is that chain of events? What's going to happen at the end of that? Because ultimately, when you build tools, you're responsible in some way, shape, or form for how they're used. And that means that you kind of have to think of design processes and design frameworks pretty loosely. And a lot of designers are actually quite uncomfortable with that, because they like to kind of lean into that intuition side of things and then just kind of say, well, I'm just going to follow this and that. And it doesn't really work that way. You know, you make stuff, it breaks, you try again, and then you give it to somebody and they use it somehow completely different, right? So, and again, the problem space could be very wide. And again, developers are people too, right? They're not just the end users, but they are users, and they have their own ways of doing things, their own idiosyncrasies, their own problems, their own, you know, everything really. So, and this is really important for looking at how you design dev tools, is ranges of use, you know, people's real lives really. And yeah, just research and iterate nonstop. And that's kind of why that first slide, that it just like rinse and repeat, right? Idea to prototype and then do it over again and keep on doing it over again, you know? And because the other thing is, like, when you're building tools, you just got to keep on building, right? You just always be building, that sort of thing. And but you have to test with real humans in the end of the day. And we need to kind of move away from what I perceive to be this bias towards just releasing and then seeing what happens. I think we need to be more nuanced with things, like actually talking to people about how they're really working, and kind of moving away from assumptions towards evidence. And I think this is the big thing, is thinking about playing fields, right? So again, you don't know what the tools people are building on top of your tools. You don't know how any of this is going to play out in the end of the day. So we have to think about kind of playing fields. Where are the borders? Where are the edges? How can we design those edges? How can we provide rules for how our things should work? Because again, the people building tools on top of our tools should be as good or better than ours, you know? So it all kind of, reputations move up and down, as we know. And, you know, thinking about this ranges of possibilities and how we can kind of do that with, you know, whether it be how the application works, how you install it. It could be one of a million things, right? And yeah, so a quick example of this is I did some work with Dijok Ayala at Protocol Labs on the IPFS mobile design guideline. So this is just an example of this idea of designing a playing field, right? Best practices. We don't really know how mobile phone devices, mobile phone applications using IPFS will work in the end of the day because we can't really dictate it that much, but we can provide best practices, right? So, yeah, you go through, let's say, this is just an example of how you could do it. You know, you'd have workshops, you would kind of gather all that knowledge, you would examine the landscape, look at all these loads of other different sorts of apps and examine them and do an analysis. This does that doesn't do that, kind of trying to start defining the problem or honing into things and start going from that intuition, you know, we got a sense about this, but we're gonna move into something else, to starting to prove stuff and designing and testing out ideas, working with other people, going in workshops a lot and kind of talking through ideas. Who is the actual user? You know, what are their actual problems, you know? And coming up with design principles and design scenarios. And that's what I'm gonna talk about primarily right here. So, for instance, we came up with these guidelines or principles, and these are just do this and everything should be fine. So, yeah, I'm just gonna move that up. Okay, yeah, fine. Can I point? Yeah, okay. Yeah, yeah, so that's it. So these are what you should think about. These are principles, right? And then kind of expanding that to kind of where it comes from research, where is the evidence, where are the insights, where do they come from, how can we prove that, you know? And then developing patterns, these are like the rules, like the ball goes outside, it's out, you know, that sort of thinking, right? But you don't know where the ball is gonna go inside the playing field. And then just some illustrations of what that might look like. Like you should probably tell that the battery's gonna run out, that sort of things. But it's good to think about the basics because often people forget about the basics. So when you give these guidelines and when people are building things on top of your things, then they have kind of an easier way of it and everybody's making better things in the end of the day. And yeah, and then how you can create scenarios. So again, what are the design considerations? What did we find out in research? We talked to loads of people, loads of different types of people. We had all sorts of different demographics, and we came to these conclusions. And what might that look like, right? And this is how to illustrate it out. So real quick, what now, right? So you should probably just ask yourself some questions, right? Because you might be building tools, but somebody has to use those in the end of the day. It might be in a CLI, but they still have to go through a process, and that process might suck. And you should find out if it does by talking to them, really. And again, how can I make tools that make people's other tools work better as well, right? And yeah, the rough version is you aren't your users. That's kind of what it boils down to. And just think about the platforms you're creating because things can happen. Lots of unexpected things, lots of really nice things. And that's it. Empathize, define, ideate, prototype, test, rinse, and repeat. And I'm over time. Thank you very much.
Yeah, so you're not your user. So if you know the problem and you solving the problem for yourself, basically as like the initial early adopter, right? Because you need an early adopter. What's wrong with that approach to taking something?
Because you will never be the only user. If you're the only user, then it's sort of pointless, right?
Well, yeah, but you have to build an MVP, right? So.
Right, yeah, but you should, okay, sorry. Yeah, but you should be, okay, let's say you have 5 users, for instance, right? You should be talking to them and not just throwing software at them, is kind of the short version of that.
That makes sense.
Yeah, okay. So it's just, and it doesn't have to be formal, you don't have to have any sort of issues, just be like, hey, what do you think about it? Not just waiting for, you know, bugs, for instance. So there's very little nuance in bugs, but, you know, having like a 10-minute conversation like, hey, Bob, I noticed you're using it, do you mind if we chat? You know, that sort of thing. So this is often helpful. So it can be super informal, that's all.
Okay.
Yep, thanks.
So, is that working? All right. Hello, everyone. So I'm Nikos. I'm a developer at WeatherXM, and I'm going to tell you a few things about what we do there, some of the challenges we're facing, trying to do all of those things, and how we're solving some of those right now. So what we do at WeatherXM is that we are a deep-in project, and we're trying to solve one of the most challenging problems of today, and that is of interest to almost every one of us. And this is providing accurate weather data and accurate weather forecasting to pretty much everyone. So to do that, we have created our own weather station, which is a station that can be operated by pretty much everyone, is accessible to everyone, and this is what collects the data. And it actually has a secure chip, it has its own private key, so all of the data that are coming out of your station are going to be signed with that private key, so everything is verifiable. You can make sure that the data you see is what the station actually provided, and they have not been tampered with by anyone. So this is the state of the network as it is at the moment. There are a few thousand stations that are active on the network, sending data pretty much every second. And you can find more details about that on the link on our Explorer, because this is dynamic. It's constantly changing as weather stations are coming in, or if someone adds a new station or they take their station offline, this is all going to change. So this is basically how our ecosystem is going to work. So we have the station owners, which are the users that are operating the stations, and they are providing data to the network. And then we have the consumers, which can be enterprises, they can be farmers, and anyone that is basically interested in purchasing and using weather data. And those consumers are going to pay to use those data, and those money, it's going to be tokens in our ecosystem. So this is what is going to be returned back to the users as payment for the data that they provide to the network. And this is a little bit of how our architecture works at the moment. So our end goal is for all of the data that we collect to be, in the end, to find their place on IPFS and to be open to everyone. So at the moment, when a station creates a new measurement, those data are being sent to us, WeatherXM. We do some processing on those data, which is basically normalization, taking out any fault data, and some resampling, which is mostly meteorological stuff. And those data are then stored on S3. And from there, we are using a tool that has been developed by Tableland, which is called Basin. And it is the tool we're currently using to put all of those data on Filecoin. And it's also providing us with a way to index those data and guarantees about storage. And the next step is data consumers, which we're going to say a little bit about towards the end of the presentation. So the two middle bullets, which is WeatherXM and S3, this is the bit that right now we're trying to make a little bit more decentralized so that it's not relying on any centralized entity for the data to reach IPFS. And this is a little bit about how those data are going to be used once they have been stored on IPFS. We're going to be running some computation on those data, and we're using Bacalhau for that, which is going to perform some algorithms that are basically creating the quality of those data, and this is also what is going to dictate how many rewards each user is getting. So, for example, if you deploy your station inside your living room, this is very bad data, so you're probably not going to get any rewards for that. So this is the way that we are going to ensure that only the users that provide good data are going to be rewarded by the network, because in the end of the day, these are the data that the consumers are interested in. And and we also have a few other algorithms like proof of location, which is basically ensuring that the station is where you're saying it's going to be. And that's all going to be public. It's going to be verifiable by the community, so anyone can go there, see the data for themselves, check the computations that we're running on those data, and verify that the rewards we're giving out and everything is correct and is in fact happening as it should. And last bit is who is going to be the end consumers of all of that data. And the most obvious consumer for us is weather oracles. So what we're aiming to do is to be able to provide all of those data in the form of an oracle to on-chain smart contracts, and they can be used for any sort of stuff. With the most prominent is probably going to be weather insurance, and that's the end.
That was a bit of a sales pitch. We don't do that here at the booth session, but that's fine. Did you have a question? Yes.
How do you make sure you don't just like put it somewhere and just
Should I put it on this or?
pour water in it, or just like use wind to get free rewards?
But I didn't get all of it, sorry. Sorry, I didn't get all of it.
How do you make sure that you don't just like pour water in the thing, or
This is, yeah, or that you do not spin the wind measurement with your hand.
yeah.
And this is exactly what the quality of data algorithm is going to do. So if you pour a glass of water over the cup, that is going to show an anomaly in the data, and it's going to be detected by our algorithm. So this data is going to be considered bad in the end, and you're not going to be rewarded for those data. And the other users are also going to be able to see your score. And the same thing is if I just spin it with my hand, this is going to show an anomaly, so that the algorithm is going to know that this is not normal behavior for the station, and it's going to give it a bad quality score.
Okay.
But these are mostly meteorological algorithms that we have a meteorologist for all of that.
Okay.
I mean, weather phenomena follow certain patterns. There is not just random water with high intensity for a small period of time. It's a bit more sophisticated.
Okay, can I start? Okay, so I was surprised today, so I don't have really slides. I'm going to talk, so I work at number 0 on IRO, but I want to talk about basically the components that make IRO. They're all crates published on crates.io and usable under a good open source license. So if you need something which is kind of related to what we're doing, but not the whole thing, you can just grab the thing and use it. We are happy if you do that. And what I want to talk about is this crate called Biotree, which is basically a different take on verified streaming. It's inspired by the Bao crate from the original Bake 3 author, Jack O'Connor, but it takes a slightly different approach. But first, demo. I want to show a few things. So I got a before I tell you how to use this thing, you should know why you want to use it. I got a big collection of data. I grabbed some movies from the Internet Archive and just want to show how fast it is to add this stuff to IRO. So I'm just adding this stuff from scratch, and yeah, this was it, 6 gigabytes in 3 seconds. And we can get it even a bit faster, but I think it's fast enough. It's rarely the limiting factor. So that's one thing. That's basically just the speed of Blake 3. Then the next thing you can do, I think Brandon showed this already, but I want to show it again. You can now run a gateway, and I have to make sure that it actually runs. Oh shit, I changed the branch. Okay, and then what you can do once the gateway is running is you can get an index, obviously, and then you can stream these files. These are some very old movies that are not under copyright. You have to go way long back until you find something which is without copyright. But what the main point is here, you see range requests which get translated to Blake 3 requests for a part of a blob. So we have one giant blob. It doesn't have any internal structure, but nevertheless, you can say, I only want offset whatever byte to whatever byte from it, and you don't need to get the whole thing. That's a fundamental difference to IPFS, for example, SHA-2 blobs, where you can only get the whole thing. You cannot get a part of a blob. You can get a part of the blob, but not in a verified way. So how does this fit into what we're doing? So there is the IRO, is the entire package. And if you just want to do bytes, if you just want to do this streaming example what I had, You can use arrow, obviously, but you can also use the arrow bytes crate. The arrow bytes crate has some networking requirements, and if you don't want those, then you can use bow3, which is just the bow streaming approach on top of the Blake3 hash function. So now I go a little bit more into detail. Sorry, it's a bit technical. Just a very short explanation how this works. Here it is. So this is how a bow tree looks. Basically, you have chunks. The chunks are 1 kilobyte. And then you take 2 chunks and make a node on top of these 2 chunks, which then consists of 2 hashes. And then you go on and on until you have a single hash, and that's the new root. And the root gets a special flag, but that's a long story. So what bow does is, at the concept of an outboard, what the outboard is, as you can see there below, I think my voice is loud enough. So basically, this is the data. This is basically the tree. So just the hashes of the chunks. And then the idea of bow is that you just store everything except for the data in a single file. Oh, that's even better. And now you have basically the tree in a very compact serialized form on disk. And then when you want to do a range request, what you do, imagine you want these 2 blocks. What you can then do, obviously, you are not concerned, you don't need this, you don't need this, you don't need this, you don't need this. So you just basically need a path from the root to the data that you're interested in. And then the data itself, obviously, because you stream the data, not the validation of the data. And that's exactly what the bow3 crate does for you. So there's a crate called bow from the original author. So what's the difference between bow3 and bow? One, bow3 is just the tree. It basically provides just the logic to describe how this tree works. And it has a little bit of I/O, but it's really not the main point. The second thing is it has async support. So if you need async, it's a bit hard if you have a sync Rust crate to have async support. And the third, and I guess the most major thing, is we have this thing called chunk groups, which means that you can imagine these blocks are 1 kilobyte, and these are 32 bytes. So the overhead, all in all, if you add it all up, the overhead of the outboard is about 1/16 of the content. And in some cases, that's a bit much. So you end up dragging around these giant outboard files. So what we do is, it's also a concept that Jack O'Connor invented, but we implemented it. We just don't store the part of the tree below a certain level. So you can configure, for example, I only want to keep this part of the tree, and I don't want to store this. So the downside is you have to do a little bit more computation, but it's very, very fast, so you will almost never be negatively impacted by that. But the plus side is that your outboard gets much smaller. So we are using a so-called chunk group size of 16. So for every 16 blocks, we store one. So the lowest 4 levels we don't store, meaning that our chunk is 16 kilobytes large, and that is kind of a good compromise. And if you use the arrow, the bow3 crate, you can choose this, but inside arrow we have just fixed it. So we are not, we don't believe in giving people lots and lots of config options. We believe in we choose a good option and you don't have to bother. We have figured out the right option, kind of. So inside arrow it is, what's going on? Anyway, it is fixed, but inside bow3, depending what you want to do, it is open. So you can configure it between 0 and whatever, some value. So just out of interest, who in the audience is familiar with Rust, or is it mostly a 1, 2? Yeah, okay, so a few people, not that few. So for arrow itself, we also have bindings, but for these crates, you would have to do the bindings yourself if you're not using Rust, but I guess if you have a higher level problem, you can just use arrow directly. But if you're a Rust developer and you have some hashing problem to be solved, then you really should consider this. And one final thing is, one final thought, so Blake 3 is the first major new hash function after SHA-2, and it adds a major new capability, meaning this addressing data inside a blob. And I really think that IPFS itself should find a way to support this, because it's such a major improvement over the status quo. And if IPFS would support this, then we would have a much easier way to interface with IPFS. So our way to do blobs is just one big blob with internal structure. And if IPFS would find a way to support this, then we could just build the bridge that Brandon showed, and directly bridge it one-to-one. But currently we can't do that because IPFS knows hashes and it has the ability to abstract over different hash functions, but it does not have the ability to use the special features of one particular hash function like Blake 3. So we are a little bit unhappy that we have to diverge a little bit there, but I feel that we don't have a choice. So it would be really great if IPFS would evolve in that case to allow supporting hashes that have these special features of seeking inside a single blob. And that's my final word.
Thank you. Next up will be the wait routine. In the meantime, any questions about Bowtrees from the audience?
So, thank you. So you mentioned how you can stream data from About Tree. Is there a way to stream data to About Tree?
Yes, so currently there is not. So currently you have to have the data and then you compute the output and then you compute the hash. But in this Bowtree crate, I'm working on something where you can do an append-only abstraction basically. So you can, let's say you have a bunch of data, you compute the hash, and then you have a bunch of additional data and you don't want to recompute the entire thing. So you just add a little bit of data, do a little bit of hashing, but only for the part that is new, and then you get the new hash. And it will be the same hash as if you would have hashed the entire thing. So that is included, but we don't know how to expose it on the IRO level. That's, by the way, that's another reason to look at About Tree if you're a very advanced user, because in IRO we don't have that yet because I don't know how to expose it in a good user-friendly way. But in About Tree it already exists.
Okay, let's talk later.
Can I have this one? Yeah, thanks. Sure. Oh, this is yours. Sorry, I put it in. No, this is mine. This is mine.
Oh, where's mine?
I can take this mic. No, I prefer this. Okay. Yeah, to like move around. Yes. Let's see. Hello, my name is Alvaro. I work as a research engineer at Status. You may know this company. It's been for a while in this ecosystem. We are building a bunch of stuff, decentralized storage, decentralized messaging. We have the Logos Collective. We also have an Ethereum client called Nimbus. But today I came to talk about the Waku protocol, which we believe is going to be the communication layer of Web3. So let's start with the problem statement. We have Alice that wants to send a message to Bob, Charlie, and Dario, right? So this is solved with a server. Alice sends this message to the server, and then the server replicates it and sends it to Bob, Charlie, and that's it, right? But as you imagine, we don't want a server in the middle, right? So there is another approach, which Alice, Bob, Charlie, and Dario, they can connect to each other directly, right? So they can send the message to each other without any central party routing the messages. So Alice can send the message to Bob, then Alice to Charlie, and then maybe Alice can send the message to Dario, but since Charlie already has it, Charlie can send the message to Dario. So Alice will save some bandwidth, some upstream bandwidth. So this is kind of solved by Gossip's app, built by Libpeer2Peer, and is one of the core protocols that Waku uses. But there are some problems that haven't been addressed, which are the following 5 problems. So we have the latency. The message propagation time depends on many factors that I will explain later on. You are also exposed to denial of service attacks. Also, what happens if your node is offline and then you are online again? You are missing the messages from the past, right? Also, since we want to scale to many people, we want people to, that runs in mobile, desktop, data centers to be able to run this protocol. So Gossip's app is not really made for resource-restricted devices, especially in terms of bandwidth. And then scalability. We want to reach millions, if not billions of people, right? So I will go deep into the 5 problems. First of all, latencies. So as you can see here, we have Alice, Bob, Charlie, and Dario again. So if Alice sends a Bob to Dario and it passes through Bob and Charlie, right? This message has 3 hops, right? So each of these hops adds a small latency to the message propagation, right? The latency that Bob will see is going to be lower because Bob is closer to Alice, right? Yes, so the latency, if any of you know Gossip Tab by Live Peer-to-Peer, the latency can be improved by this so-called deparameter. But the latency also depends on the amount of nodes in the network. The more nodes in the network, the more latency that you will have. So here we have the trade-offs that we have. More nodes, more latency, which is bad. More D, or higher the D, lower the latency, which is good. But higher D means also higher bandwidth. This will mean that your node will consume tons of bandwidth, right? And then the last trade-off is the more message size, more latency. Because if the message is very big, then the time that it takes to transmit, to be transmitted, then it's going to be higher, of course, right? So yeah, we are also exposed to denial of service attack, because what happens if Alice starts sending messages to everyone, right? So this is fixed in a centralized environment in Web 2, but doing this in a decentralized way, it's a bit more complex. Well, you get the idea with all the messages. Yeah, what happens if your node goes offline and then you are online again? Then you have to fetch the messages from the past, and you need someone to provide you these messages, right? By now, we use a simple database, but we are exploring other alternatives, like, for example, IPFS. And yeah, as I said before, we want people on mobile, desktop, laptop, whatever, to run this protocol. And yeah, last issue, scalability. The network should scale, right? So yeah, we want to scale to many, many, many people. So what's Waku? Okay, Waku is the protocol that is being built by Status, and it's being used by different companies right now. We have an open testnet that you can join, and aims to solve all these 5 problems. But how? So first of all, we have latency, right? We solve it limiting the message size. We also have found a trade-off that we believe is the best one between D and the bandwidth. Denial of service, we are using a decentralized rate limiting protocol, which is called RLN. It stands for rate limiting nullifiers. It's based on zero knowledge proofs. And we also have some peer scoring that will kick a bad peer. For offline nodes, we have the store protocol. So if you're offline for some time and then you're up again, you can use this store node to send you the messages that you missed. For resource-restricted devices, we have light clients. And for scalability, we are sharding the network in multiple shards. I would like to share with you some research highlights from the last months, weeks, which are the propagation times that we have right now in Waku, simulated in a real environment, and also the overhead of RLN. If you remember from the previous slide, I said it's based on zero knowledge proofs, so the generation and verification of these proofs will add an overhead in the pipeline of latencies. So regarding the propagation times, long story short, it's impossible to give a single number on the propagation time because each node and each message will see a different latency. So with these numbers, 1,000 nodes, D equals to 6. If you remember the Gossip subparameter, and a message size of 100 kilobytes, we have a latency of 800 milliseconds, average latency. And these are real simulations with Shadow, a tool for simulation, for network simulations. Maybe you know TestGround, Kurtosis, or these other tools. These simulations use RLN. They also simulate a latency of 100 milliseconds between each node. And the bandwidth is also limited on 80 and 40 megabits per second, up and down. So as you can see, the simulations are quite accurate. And yeah, the last highlight, TLDR, the proof, the zero knowledge proof that we have for RLN, the proof generation time is constant, no matter the size of the message, 0.15 seconds, which is kind of okay. This adds to the whole pipeline of latencies. And then on the right side, we have the proof verification time. It's also constant, 0.012 seconds, which is quite low. And this is added by each node. So if the message travels 5 hops, then you are going to add this latency to each hop. And this is my last slide. We have an open testnet that you can join at any time. It's based on Ethereum Sepolia, which is a testnet, an Ethereum testnet. We use this for the decentralized write limiting. So if you scan this, you can join. We haven't announced this publicly yet, so this is a bit of an alpha leak. And we are hiring, not only in Waku, but in the whole Status company. So if you want to join the team, feel free to talk with me after this talk or scan this QR code. That's it. Thank you so much for your attention.
Okay, next up, we have Wander. But we have a question in the meantime. Okay, cool.
Thank you very much. Great to see numbers powering protocol design. Can you tell a little more about this Shadow network simulator? So I'm asking with the background of, could this also be used to simulate things like gossip sub or anything? Or just give some words about the Shadow thing.
Yeah, definitely. So actually I have some friends working in the NIM lib peer-to-peer implementation that have used Shadow in lib peer-to-peer and gossip sub, so you can do it. But the worst part of Shadow is that it doesn't measure CPU time. So all these latencies that we are adding like a fake await with the times that we know that RLN adds, right? But if you have some very crazy cryptographic thingy that takes a lot of time to execute, Shadow doesn't really take that into account. So it's more focused on the networking layer. As you can see, you can simulate latencies, you can simulate constraints on the bandwidth, you can even simulate package drops and so on. But answering to your question, I have friends in Status using this with Gossip Sub, and I can put you in contact.
And it's also open source?
It's open source, fully
Okay,
open
cool.
source.
Yeah, awesome.
Yeah.
Cool, thank you.
I'm built in Rust. I think someone before mentioned Rust.
Quality property.
Calm down.
It's gonna happen. Yes. Yes. Yes.
Oh no, it didn't do it.
Yeah. My screen is gone now. Great. Oh, this works. Can I have a microphone? Apart from this one? Oh, okay, this works. My name is Doruk. I'm a 19 years old university student. We have a startup called Dorkodo. Oops. It's crashed. I will try again. Sorry. So I will summarize what we are doing here. We're working on We are working on a social and decentralized knowledge protocol called Wander. This is our logo. So let me start with our problem set that I believe you are already familiar with. We want a real-world P2P internet of users, not developers. Also, we want a self-sovereign user agency, and by user agency we mean identity, data, and social circle. These should be owned and controlled by users, not public, not centralized companies or services. We want interoperable apps and services. We want reusable, composable, and self-certifying semantic data, and pick up what Web 3.0 movement kind of failed to go into the mainstream with their semantic data thing. We're trying to do this with the help of other protocols and technologies that overall developed in the industry in the recent years. Also, we want local first, offline friendly, and censorship resistant value and data publishing. And no more walled gardens. This was our goal. We first started as 2 kids in our rooms, trying to build some, real-world apps. We had some ideas for them. But we wanted to do this in a decentralized and user-owned way. We didn't just want to become one of those Web 2 companies. So instead we started to working on the technology to enable that. There was already some building blocks ready to go, but there was a missing point that we believe for it's really hard for a traditional developer, a conventional developer, to pick up Web 3 tools and build a product with them. So what we're doing, this is Wonder, in simple words, user agency. How can we enable that? First, we have documents and events. Documents are how we store data. They're like IPFS blocks. We have metadata, public, and data and event in a document. And these documents are just like regular objects that you store in your application. And we have events. Events have IDs, kinds, just like Noster. I don't know if you're familiar with that protocol. One of our principles was that we didn't want to reinvent everything from scratch. We wanted to build on top of the existing building blocks that are already adopted and make them mainstream or easy to use with our SDK. We are a protocol first. We are trying to build a protocol first SDK with that. So what is our network structure? Here it is. You're an average user. You use probably many apps now on your phone. And I just sketched these over the back. Sorry, I didn't have a pitch deck or beautiful looking slides, but I hope it's clear enough. You're a user, you have a private key, that's all good. We are already familiar with that. But that's not a real world user now is very accustomed to. People want freedom, but they just don't care or understand enough of the technology. So we are just trying to make this also easy for users. We are trying to make this easy for both developers and users in the aspect of experience. So you have many apps, X, A, B. There can be an infinite number of apps, but they're just user interfaces. Under the hood, they use a client, and that client is our SDK, and it sets up a peer. A peer is it both supports P2P and the classic server-client architecture. We store personal data on pods, on things called pods. These are like your accounts. All your data, your decentralized identity, it's all stored safely in your pod. And that pod is much like a GitHub repo. This is the local part. We have clients and peers. They're just like the same thing, but clients are much more powerful abstractions, tools that everyone can use, just like a file browser or a web browser. But applications, they provide beautiful user interfaces and experiences for those actions, your regular actions. We have something called seeds, and their main purpose, they're just ordinary peers, but their role in this network is provide data and value to the rest of the network. There may be different seed implementations. Anyone can run a seed on their computer, or services and companies can do that. And your pod is remotely synced to one of those seeds that you, as a user or as a developer, add the seed's address to your app or to your code. You add a seed, and your pod, your all data securely synced to a seed on the global network, and these seeds by default are compatible with Noster, IPFS, and the World Wide Web. Also, we want to add more protocols and standards and other networks, other ecosystems to make this possible, so that we're not locking you in. Any seed will be by default a Noster relay or an IPFS node by default. This is what we are trying to do. This is the overall architecture. A little detail about pods. For public data, we distribute events as event feeds to seeds, Noster relays, IPFS network, and as RSS to the World Wide Web. For private and personal data, we already stored this on a pod, but for secret data, we keep it encrypted, local first, and P2P synced. But open data is public, is stored in the public index of the pod. So we are building this open source. We're just in the discovery experimental stage now. The code is all on the open source on GitHub. You can, if you're interested in the idea, or if you believe we have some mistakes, or if you have some recommendations for us, you can reach out to me at dork@dorkodo.com, or you can visit our website or our GitHub organization page, or hit me up on Twitter, X. Thank you. If you have any questions, I will be here till the end of the day. We can talk. I'm open for any ideas. Thank you.
Working? Yeah, okay. So do you have any plans? I think one of the problems with one of the problems with applications in the wild is like you have a schema for your application and it ends up evolving, and that is a very gnarly problem. So do you have any plans about schema migration?
We're already supporting IPLD and multi-formats for that. Also, we, as I said, we have a metadata on documents, and in these metadata are just like HTML pages. They're open, and you can have a link to your data schema, and the application, the code can, or any external app, a third-party service code can have access to that schema and fetch it, for type completion, etc.
Okay, thank you.
You're welcome.
Thank you. Okay. Hello, everyone. My name is Dennis. I'm part of ProbeLab. ProbeLab is doing network measurements and protocol optimizations for the IPFS network specifically. And we are part of Protocol Labs at the moment. Just 2 words or 3 about ProbeLab itself. So we are doing network measurements and protocol optimizations, especially, as I said, in the IPFS network, but also Falcon, for example, and mainly the P2P-based networks. And the picture on the right depicts what we actually think how things work. So you might think things might work, but probably or sometimes not as you would expect them to work. And so I think this picture depicts this really well. And in this talk, I wanted to talk about so what has happened in the past year, so in measuring the IPFS network and what the probe lab specifically has done in the past year. And I want to highlight 4 different projects here. And afterwards, I will show some just long-term trends, what has happened in the IPFS network or IPFS DHT over the past few months. So a project that Probe Lab has done, or something that we have uncovered in the beginning of the year, is a major DHT network incident. So there's also a blog post about it. We found out through network measurements that around 60% of the network, or 60% of the nodes participating in the DHT were unreachable. And for better or for worse, no one noticed. Which is a good argument for decentralization, because I think in any other centralized infrastructure, if 60% of the infrastructure goes down, you would definitely notice. And the only thing what we found out is that there was a latency spike, so DHT lookups were a little slower, DHT puts were a bit slower, and so on. We identified this configuration error and encouraged the community to upgrade their Kubo instances and nodes in general, and we saw afterwards that the latency went down to a steady state then again, starting in February or so on. And another thing that we did around the same time is we measured the performance impact of the Hydra boosters. I'm not sure how many of you are familiar with the Hydra boosters, but the idea of Hydra boosters is we place a lot of Kubo or like DHT servers into the DHT key space to receive all the provider records in the network so that we can serve them back to the network at any point in the key space and thus accelerate the lookup performance and publication performance as well. And we found out that the latency gain that we get by operating these Hydra boosters is actually in the order of perhaps 10% or so. And this didn't warrant the costs that they incurred on Protocol Labs bill. So it was around 1.2 million per year. And so we decided to shut them down. And we could shut them down without worrying that the network will fall apart or that we would gain another, I don't know, 1 second or so latency in DHT lookups. So this is another project that we did. Then another part on the latency gain side is, I'm not sure if you're aware, but if you put something into the DHT, at least 2 years ago, and even 1 year ago, putting something in the DHT took around, let's say, 30 seconds, sometimes a minute, sometimes even 2 minutes or, to write something into the DHT. And so in the last year, when the network got a little more mature by having more stable nodes, this naturally went down to around 6 to 7 seconds. But we at Probe Lab designed a new algorithm which we call optimistic provide, which is doing a few things differently. And without sacrificing availability of records in the DHT, we actually brought it down to less than a second. And so in this case, it shows second values, but this is only because we are showing like the 95th percentile in this case. But the average case is way less than a second. And then on the bottom right-hand side, we have LibP2P improvements. So we ran a large-scale measurement campaign on hole punching. So how does NUT traversal work with LibP2P? And we figured out a few different things that could be improved in the protocol, which then could flow back in DCD in a version 2 of this hole punching protocol. So these are just 4 things that we've worked on over the past year. And I brought a couple of slides which just look back over the year. So how does the network how has it evolved over the past few months? And so what we can see here is the date on the x-axis and the number of unique peer IDs that we find in the public IPFS DHT, which is now called the Amino DHT, so just so you know. The blue line is the total number of unique peers, and the green line shows the number of peers that are actually online, and the black line at the bottom shows the ones that we consider offline. And then there are some spikes that you can also see, and these are just measurement artifacts. And what we can see is that in the beginning of the year, we had like a slow increase in peers or nodes joining the network. Then we had a plateau, and then during May this year, there were some 2 steps where we gained around, 10,000 new peers within a few weeks. Then we had a long, steady state again, and in the middle of last month, we had the sharp decline, and a lot of nodes, around 7,000 nodes, left the network. And let me skip this slide for a second. And if we look at the agent distribution, so if we want to know which nodes have actually joined the network and which nodes have left the network, we can see here that in the middle of October, we see this huge drop in agents of the Kubo 0.18 version, which shows us, okay, mainly Kubo 0.18 nodes have left the network. And this in general shows us just the number of unique agent version, or like the number of agents in the network. So the graph that we've shown previously, but just split by the number, by their agent themselves. And so this shows the same data, but just split, or like this shows the share of which agent versions are actually deployed in the network over the past year. It's a bit difficult to see. A lot of stuff is going on. But here we can see at the bottom left, these are the Hydra boosters. At the top left, you can see that the Hydra boosters are the solid blue color, and we can see that they were running at around 2,000 nodes at the beginning of the year, and then we decided to shut them down. And so in the beginning of April, we slowly phased them out here. So this is part of why what ProbeLab has ProbeLab has suggested to do. And then across the whole year, you can see that this dotted orange area here is the 0.18 Kubo version, which is by far the most popular to date still, and throughout the whole year as well. But then here at the end, we can also see that we have like this gray version coming up, which is Kubo 0.22, and some other new Kubo versions as well at the end here. And if we look at these newer versions, we can see that this is like the community uptake. So this just shows the Kubo version 0.19 to 24, and again the date in 2023, and the number of peers that actually run these Kubo versions. And we can see at each time when the new Kubo version was released, there was a steep uptake. And what we also can see here is this wiggled line, which is like a daily periodicity. So this shows us that these new Kubo versions are mainly adopted by, I would argue, residential, not mainly, but also updated by residential Kubo nodes, which have like this daily periodicity. So they shut them down at night and turn them on in the morning again. Because if you look back at this graph, even though you have this little wiggled line here, it's pretty stable. So most of these nodes in the network are actually run by pretty stable node providers, I would argue. And yeah, then we can also see that every time a new node version, a new Kubo version is released, the previous version goes down, which is also expected. But what actually would be better is that not the previous version, which is a newer Kubo version, goes down, but also that one of these like quite old versions, they're not particularly old, but for example, it would be great if this Kubo 0.18 version would go down significantly if a new Kubo 0.24 version was released, for example. So these are just a few insights or a few things that we can see from this data. And yeah, these are just a few graphs here. I think I'm running out of time. We also measured the retrieval latency continuously over the year. And just to give you a ballpark of how the retrieval latency looks like, the P90 retrieval latency of looking at provider records on the DHT is around 400 milliseconds from the EU. The same stuff we also measure for the interplanetary network indexers. And here we can see that in the uncached version, a lookup in the network index is roughly twice as fast. And in the cached version, it's more than an order of magnitude faster to look things up in the network indexer, but you sacrifice the decentralized nature of things. Then again, the publication latency is in the order of 15 to 20 seconds in the, again, P90 case from the EU. And this optimistic provide algorithm that we've designed at ProbeLab actually can bring this down to only a few 100 milliseconds. And then there's a third algorithm which trades off a kind of excessive resource consumption by crawling the network and having a full routing table. So this is this full RT here. This is even faster, but at the trade-off, having like excessive resource consumption. So depending on your use case, you would rather use one or the other. Yeah, and this optimistic providers right now is still an experimental flag in Kubo, but I think it works really well, and as you can see, the speed up is significant here. Right, yeah, and to close, so the ProbeLab roadmap consists of looking at IPNS. So from the community, we sense that IPNS is still something that is very much a pain point because it's not fast enough, or you cannot look up the records very well. And I think the stuff that we've developed for this optimistic provide that I just showed you can also apply to IPNS, and we can have good latency improvements there. Then the second one would be Gossip Sub that ProbeLab wants to look into in the context of Filecoin and Ethereum, the like. And the last bit is libp2p bandwidth requirements, because during our Hydra booster study we found that when you do a lookup at the Hydra boosters, the amount of data that you transmit, 95% of that data is just the handshake and exchanging metadata. And the actual payload only is around 5% of the data that gets transmitted. So I think there's also something that we could improve here. Yeah, and we're fundraising. So if you want to become a backer of this roadmap and your company or your project would benefit from insights into this and into improvements of this, become a partner. And yeah, that's it. Thank you so much. Yes, go ahead. Oh, sorry.
So you mentioned the hole punching statistics. I would be interested in what is the hole punching success rate, and is it different for TCP and UDP?
So yeah, this is something that so the tribal knowledge is that UDP hole punching is supposed to be easier than TCP. This is something that we didn't find in our measurement study. So UDP and TCP success rates are roughly the same. So I would argue UDP is still a bit better, but probably part of, you could easily explain this with the noise of the measurement. Then the overall success rate was around 70%, and this is across all kinds of different routers. So if you have a router that is so that you can hole punch, the success rate is much higher. But so this 70% applies to the population of all routers that participated in this measurement study. And what we also found is, so in this DCUTR protocol, so this is the hole punching protocol, you actually do 2 retries. So you try it once, you try it twice, and the third time as well. But what we found is if it doesn't work the first time, with 99% or 97% probability, it won't work the second and third time as well. So this is one thing that would flow back into the protocol design again. Do a different approach in hole punching. There are different approaches, and so with the second try, do something else and just not do it again. Cool.
Okay, thank you.
Can I get a study? Okay, thank you. Hello, everyone. My name is Tao Shen. I come from China. Can I ask a question about, have you been to China before? No. Is there anybody have been to China? Did you heard of jiaozi? What is jiaozi? Yeah, dumplings. Any other more? Yeah. Jiaozi is basically pronounced as same as another meaning in China. It is the first meaning is dumpling. Yes. Another meaning is the earliest paper money in the world. The first paper money in the world. Okay. Today I want to introduce Jiaozi FS, another implementation of IPFS. Basically, it's focused on the version control features or has a data versioning primitives inside to build a data versioning file system for many use cases. For example, machine learning pipelines, AI pipelines, and configuration management, use cases. Okay, let us look back to the Kota Corporation. I think everybody here knows the Git, yes? And the GitHub. Yes. Thank you very much. You can see the parts, after computer born, you can see lots of different generations of Kota Corporation. the most famous one is Git. Git is good at code corporation and programming, and especially for the code world, it's very famous. But for data corporation, firstly, data is any collection of bits of value. But for the past many years, maybe 10 years, as far as I know, in China, lots of big gains of internet components. They have a very, very huge data size and a huge distributed storage like Alibaba Cloud. And lots of internet components, they have their own data centers with distributed storage, distributed file systems, like a Google file system, many different implementations of Google file systems. But the data corporation till now is still copy and paste. If you want to make a corporation with some data size, you need to copy and paste the data size. As you can see here, the Hadoop IPFS and Amazon S3. But how can we make a data corporation better? That is why we want to build JAWS-FS. And the data is not most of the time, data is not standalone, just code or just data, because code is another kind of data. For example, data models of machine learning and AI. Sometimes code is with data, sometimes data is with code. So in modern time, for the modern data analysis, we need to think of how to make a corporation with data. How solutions work for code and data today? Yes, there is already exists some data corporation solutions. For example, the Git large file system. It is good fit for Git. It's integrating very well with the Git, GitHub and the Git. But it's not enough because we want to build over IPFS open standards. For example, CADs and lots of specification, for example, routings and cooperation with other nodes. So in JAWS-FS, you can see this structure of different layers of the implementation. We can, at the bottom layer, we have the Git server, Git-like server data management for the data size. For example, you can think of that push, pull, commit, and branch, for example. But we don't want to fully support all the command size of Git. Think of that, Git is for code, it's not for data size. Especially for the machine learning data size and the AI modeling is very, very big, very, very huge data size. It's not feasible to set up your own staging repository. So not everything is good like Git, command size. But we will borrow most of the ideas of the Git server. And we have implemented polytree indexing for the content addressable data size management or storage. Maybe you have heard of polytree in other sessions. We have our own polytree library implementation. You can get it from our GitHub. And it is indexing over the content addressable data size to make deduplication of the data size. Think of the different version of the data. Most of the data is the same, but you have a different dirt of the modification or different version of the data. That is, the difference is just the dirt. So we need to save the space of the storage. So we want to use the content addressable block management and with high efficiency indexing over these data size. Data blocks. And over this storage layer, we have command line and SDK and UI for different use cases or applications to use the JAWS-FS. We can extend to, we need to integrate the many SDKs to integrate with the Web 2 computation frameworks. I call that is extension. Based on that, we can build a Web 3 Hugging Face. We call that Data Hub. Think of that GitHub is a data hub. Compared to the GitHub. Okay, this is a picture of architecture of JAWS-FS. Basically, here is the JAWS-FS server, and we have the metadata and the data, and we can also integrate the other data sets or on-premise data sets to be managed by the server. And we can have SDK and a client to integrate the other computing frameworks. Okay, the use case, first is we can build a Web3 Hugging Face. And we can build the data versioning for the modern data teams and platforms. And we can build the data versioning for end-to-end machine learning pipelines. And because we follow the principle and the standard specification of IPFS, we can build a different version of the data NFTs for the models and output of machine learning. So you can monetize your output. So that is, we call that data versioning for Web3 data economy. How to monetize? We have two directions. The first direction is for enterprise. It's production machine learning pipelines. The second is Web3 data hub. That's all I might share. Thank you very much. Please feedback to me. Thank you very much.
Perfect time. Yes, question at the front. And meanwhile, yes, we got our answer. So you said you make use of deduplication of 1 megabyte blocks. I might find it a bit hard to imagine that machine learning models, which are basically just random weights, even if you do a new training round or something, that they're in any way that the data, that 1 megabyte chunk of that will ever have another megabyte chunk that is identical. So do you actually have any, storage saving from this deduplication or not?
As far as as we know, IPFS is famous for deduplication solutions for the industry. Yes, I found that that is not enough. Yes, as you said, that is the difficult part. We have put a lot of effort on this part to manage huge megabytes of data size. But the details I think is a little long. So can we think offline? Can we talk offline?
Yeah, sure.
Thank you very much.
Yeah, I can switch.
If you can do it closer to the end, then I can figure out if it's possible or not.
Okay.
Yes.
Okay.
Do you want to use this?
Oh yeah. Oh.
You can
Yeah.
use this.
Okay. Hi everyone. I am Secured Finance founder Masa. My company is in Switzerland, but I'm from Japan. And Secured Finance is a DeFi project, and everything on-chain and fully decentralized. And it's very important financial infrastructure to make time value of money into crypto. At this moment, crypto doesn't have this time value of money concept, and we are building yield curve and then achieve a fixed rate interest rates market. Everything on-chain, and actually our web application is using IPFS and deployed through Flake. And I really love IPFS, so I'm not only
finance guy, but also I'm a computer science, and I really like IPFS, and I have some contribution to the IPFS community, and that's why I'm here today. So actually, I made it two announcements. So one of these announcements is I actually have been working on translating the Chinese version of IPFS textbook published 3 years ago. And it took me 3 years translating Chinese into native Japanese. I don't speak Chinese. That's why it's so difficult. But this is very important to foster Japanese developer community. So it's actually just published this week, or last week. And so I'm so happy to share this kind of a contribution and then, you know, long-term commitment. And then finally came out, it's sold in Japanese all over Japan, also Amazon.co.jp. And what's most like exciting to me is, as you can see here, it is, you know, located next to the esteemed Mastering TCP/IP textbook. So, you know, the IPFS is now considered to be is kind of a very important protocol. So yeah, that's I'm so excited to see. And recently I find out, well, this is a photo, but in a tweet, you know, this is like this. You know, if you go to Japan's like a bookstore, it's features like this. So it's very, very exciting to see it's really happening here. And this Shosen Book Tower is in Akihabara. There's a really big bookstore. And actually, this IPFS book is bestseller within the computer books. So I'm so excited to share this fact. It's bestseller in Japan. So yeah, I'm very excited. So I just want to share, you know, I added a little bit of the, you know, a flavor, like a more, you know, graphic thing, like Academia DHT, like a graphic. Oh, let me share the actual thing on the book. Yeah, it's basically more like expansion of IPFS white paper and IPFS and Filecoin white paper, and yeah, I can add a lot of like a graphic aspects, and yeah, something like this, and also I created some. Let's see, it's everything on IPFS. Let's see. I think it should be here. It takes. What was in? Okay, I'll go next, but why it doesn't?
Yeah, no, IPFS doesn't always work.
Ready? Okay. And another one is actually, yeah, I hosted the, you know, how IPFS works, like workshops, and then Steven, you know, show up and then talked about how IPFS works. And the fact is, you know, this video is 2 gigabytes, and it's work perfectly, and it's I can play here. Okay. Yeah, so yeah, it works for even 2 gigabytes of the size, so it's super amazing to see it. So yeah, this is a fact. And oh, can I play the video? Yeah. So yeah, this is my contribution to the IPFS community, and as a DeFi founder, I just want to make a big announcement that we're going to main it live December 15th, just 1 month away. Starting with global itayose for book building, and 2 weeks later, we open up the global bond market for crypto, which doesn't exist at this moment. So we are so happy to share the bond market with you, run by IPFS front end. So please join at December 15th. And if I have 2 minutes, I'd like to basically play kind of like an introduction to secure finance, if I allow. Okay.
In a pretty deep way, Web3 and crypto represent this amazing opportunity to rewrite the rules in how economies and governments work. And so it's a combination of computing and the power of the computing platform.
But the finance market is larger, much larger, and clearly we are missing our capital markets. And as a secure finance, we want to extend this maturity to longer, let's say 5 years. I realized change needs to happen when I saw a LIBOR scandal where a group of bankers manipulate the benchmark interest rates that's governing a $1 trillion scale of market. That's the reason why I decided not to go back to traditional finance.
What's missing in the DeFi space is clearly the yield curve, which is considered to be a continuous plot of interest rates over a time axis. We can build yield curve for any currencies as long as we have strong economic demand.
What first impressed me about secured finance, I think, is the team's level of professionality and level of knowledge. I worked at Goldman Sachs for 11 years. GSR is a trader, investor, market maker, and ecosystem partner. I think the future is very bright for institutional entry into crypto. The user won't be just merely seeing one number, getting the feedback in terms of what their yield would be given different risk factors, and be able to produce a lot more diagnostics on the success of their lending profile.
Secure finance is for many different users, from retail to institutional. By combining blockchain technology and traditional finance, we can actually create a better platform and a better world.
The future of finance is here.
Right. Thank you very much.
Okay, that actually brings us to the end of our session. Is there anybody here who's expecting to present who didn't get a chance? Awesome.
No one.
Perfect. We only went over by 6 minutes. Nice work, everybody.
Thank you.
That's it. You're free to go. I think there's coffee and things like that in the other rooms, and then the next set of sessions starts in just over an hour, or just under an hour.
All right. Hi, everyone. My name is Joel. And today I'm going to be sharing basically a lot of experience from working on IPFS for the last 6 years or so. And in particular, I'm going to be talking about how we can build systems for mutable data on top of IPFS. So if we think about IPFS, isn't the immutability the point? Like, we want to be able to know that things haven't changed. That's sort of what we get when we put files into IPFS. We get a hash of it, sometimes referred to as a CID. However, this basically means that every time we update some piece of content, we get a new hash, and we don't have a way to keep track of the changes that have happened over time. IPNS is a system, sort of like IP naming system. It's a system that allows you to essentially have a way of having mutability. However, it doesn't really go far enough. There's a bunch of properties, which I will mention later, that we don't really get with IPNS. And blockchains are great for more sort of financial use cases, but they don't really do the type of scalability we get with something like IPFS, where we can just have data living at edges, and we don't need everyone to replicate the data of everyone else. So what are some of the requirements we have for mutability in this type of decentralized environment? Well, first of all, we want something called self-certifying authority. And that's basically the ability to know when I synchronize a piece of data, that that piece of data actually comes from the source which it claims to come from. So for example, if I author a piece of data and send that to you, you can cryptographically verify that that is actually coming from me directly. It would also be nice if we can do collaboration and conflict resolutions on top of this mutability system. And finally, access control, so that we can control who can update and modify certain objects. And so why do we need this mutability system? Well, we want to be able to build different sort of databases, whether that's web scale, similar to Web 2-like databases today, or we want to build more peer-to-peer databases that maybe live completely in the browsers and are sort of gossiped around nodes directly. We might want to have data feeds that are sort of dynamic and high traffic. So that could be from capturing vehicle data or weather data or all kinds of different types of places where we just output a lot of data at the same time. We also could use this sort of mutable system for compute pipelines, so how we can tie different computational networks together. And so there are actually a few efforts that have been trying to do this over time in the IPFS ecosystem. So OrbitDB is one fairly well-known one. And Query is one that is not really around anymore. To the right here, you have Blue Sky is probably the one that's most deployed right now, but it's very focused only on social networks. It's not really general. There was an effort called IPDF, which was also trying to build this very generalized version of a data feed. But none of this have really completely taken off, and then they have different trade-offs. And they don't meet all the requirements that at least I had when I wanted to build things on top of this, or create or build with some sort of mutability layer on top of IPFS. And so what are those requirements? Well, first of all, authentication should be easy. if a user comes to an application, they shouldn't need to like set up some new kind of wallet or think about how they manage their keys. That should just seamlessly be handled by the application and implicitly by the protocol itself. Key rotation is an important aspect, and tamper resistance, those are kind of like very bound together. So basically what that means is I should be able to see when a key has been rotated out. Everything that was signed with that key before it was rotated should still remain valid, while things that are signed with that key after it was rotated should obviously be considered invalid. And tamper resistance means simply that if something was authored at some previous point in time, I don't want the author to be able to go back in time and change that data or add to that data in sort of like a malicious intent way. Finally, we need this mutability system to have data synchronization. So we want to be able to synchronize it across nodes, and that could be in very, very different settings. For example, it could be in a peer-to-peer way directly between browsers or users' local computers, or it could be in a peer-to-peer way between like servers and like larger scale deployments. And so, yeah, I'm basically going to dive into how we're solving these problems with Ceramic. And so Ceramic is the protocol that I've been building for a few years, and I've basically drawn upon all of these learnings that I've had over the last 6 years in the IPFS ecosystem. So first of all, authoring data. I think a key thing to realize here is that users generally already have wallets that are cryptographically enabled. That could be like a cryptocurrency wallet, where basically you probably have some extension or some mobile wallet that holds a key. But there are also things like passkeys, which is this new standard developed by some of the larger companies that are making phones or browsers that basically allow you to do sort of a single no password sign in to any type of Web2 service, but they could also be used to author data in the Web3 sort of context. And one thing I've discovered recently is that newer passports actually also have a cryptographic key embedded in them that you can use to author data with. And so, for example, you could delegate a key from a passport to a session key and basically author data on behalf of your identity. And you could sort of wrap that up in a zero knowledge proof so you don't disclose any personal information about who you are. And in order to make this work seamlessly, if you think about, if you ever used like a Web3 blockchain, you realize that every time you make a transaction, you need to sign a message with your wallet, you get a pop-up. If you're using like a feature-rich application, you do a lot of interactions, you edit content and so on. You don't want to sign a message every time you make a small edit or you make an upvote or anything like that. So in order to solve this problem, we're using something called object capabilities, or OCAPs for short. And we're using a format called Cacaos, which is basically a way of wrapping different object capability formats. So currently it supports signing with Ethereum, supports UCANs, supports passkey authentication, and it's like really extensible in that way. So what does the UX flow look for like when you do this? Also, suppose the user has some wallet, they come to the application generates a random session key. This session key can actually live in the secure enclave of the browser. So there is this web crypto API that allows you to create a key that's not extractable by the application context. Then the application basically sends a message to the user's wallet saying, hey, can you give this session key permission to write to this resource on behalf of the user? And so the user signs this message. Most commonly, sign in with Ethereum is used. And this message basically contains the resource URL that the session key is allowed to edit and write to. Now, once the application gets a signed message back, the application can use the session key together with the signed message and invoke and basically like make edits on that resource. And as long as the session key signature is valid and the signature in the object capability is valid, you can sort of prove the whole chain from the user's account, which is the ID PKH in this case, that controls the resource. And you can see sort of the full chain back to the session key that actually is trying to edit the resource. And so this is sort of like the minimal example of this, but you can see like how this can enable a good user experience. But object capabilities are really powerful. You can use them to essentially create longer delegation chains and basically delegate between multiple users and so on, and have like basically ways to limit the capabilities as well. So let's talk about the data structure of these event logs that we're using in Ceramic. This is kind of the high-level overview. You can see this linked list here is basically a hash-linked data structure that's stored in IPLD. There's an init event, that's basically the event that creates this event log. There's time events, which I'm going to talk about a little bit more later. The data events is basically just like updates, signed updates to this event log. So let's double-click on the actual data structure of this, these events. So you can see here we have the init event to the left and the data event to the right. So it has some header, basically a controller that says who is basically allowed to author data into this event streams, and then there's a piece of data. And then you can see there's another structure right below that that's called GAWS, and that basically is another structure for encoding the signature. And then we have a very similar thing on the data event. The data event also includes the ID of this event stream, which is basically the hash of the initial event, and it has a previous pointer, so you can have this like linked list type of structure. And similarly, this data event also has this signature that's like detached and is separate, and this points to the payload itself. Okay, so like this is okay, like it serves the purpose, but it's not optimal. Like it's not easy to understand what's going on here. Why are there like these two different events and so on? It would be nice if I just had one piece of data with a signature that just represents an event. And so we've been working on this standard called VARSIG together with Fission and Spruce. And this is done in an organization called Chain Agnostic Standards Alliance. And VARSIG is a really neat way to encode signatures. It basically allows you to encode any type of signature along with an IPLD object. So the way it works is that the signature itself is encoded as a byte string, and it has a codec for which key was used to author the signature, and it has some additional sort of parameters for that key type. Then it has an encoding codec, which basically tells you how to take the data and encode it as a byte string before you apply the signature validation algorithm. And then there might be some addition, or rather at the end, you have the actual signature bytes. And so how this is used in practice is that, for example, if we have a JWT signature, we can take the JWT object, encode the payload of that JWT as an IPLD object, which is just like JWTs are JSON essentially. And so when someone synchronizes an object, they can see it's like a pure IPLD encoded object. So it's like similar to the, say, init payload here. And then there's an additional property, which is basically signature. And you take the bytes out of this VARSIG, you look at what the encoding is, you take the IPLD object and you encode that. So in this case, it would be like a JWT encoding. And so you take this JWT encoding, encode the IPLD object as that, and then you know how to validate the signature. And the nice thing about this is we can encode essentially like any type of signed signature format. So JWTs is one. We can encode Ethereum signed messages. So there's two different standards here. One is 191, the other one is 712. We can encode W3C verifiable credentials. We can encode, this new IETF also has a separate verifiable credential standard. But it's really like no limit as to which types of signature you can match this. So this basically makes it possible to append a signature to any IPLD data using any signature format you want. So what this means for the data structure in Ceramic is that we can essentially simplify the data structure I showed before, where the init event is just a header, some data, and then the signature is a VARSIG at the end. And similarly, the data event is just like the same data we had before plus the signature. And this is just like much easier to work with and much easier to understand what's going on. Okay, so next up, I want to talk about tamper resistance. So how can we ensure that the data that's been added to the system has not been tampered with? Because if it's just a single file, it's easy, right? Because if someone has tampered with the data, the hash doesn't actually shake out. We get a different hash, and we know that someone tampered with the data. But if we have this event log of data, and someone creates 2 alternative histories, how do we actually know which of those histories is the legit one or which one was authored first? And here we can see, like, yeah, we actually want to know when this data was published. And I mentioned the object capability before. These object capabilities are normally created with an expiry date. So maybe this object capability works right before 5 o'clock, and right now it's 4:30. So if I author the event right now, yeah, it should be fine. We can see that it's valid. But if I author an event using the same object capability an hour from now, it's obviously not like valid. So that should not be seen as valid. But if I synchronize this data structure, 2 days from now, I don't really have a way to know which time the event was actually authored at if we don't have some type of external source of time. And so this is where we introduce the concept of a timestamping system. And essentially what this is something we're calling a blockchain anchor. So right now, we are running in what we call an anchoring service. And the anchoring service takes a bunch of events that have happened in the network, builds a Merkle tree, and sends one transaction to the Ethereum blockchain, which basically timestamps all of the events under that Merkle tree at a particular point in time. And so you can see that represented here. Here's the Merkle root. We send that to Ethereum. And here at the bottom, we have the events that was actually included. And so the time event, basically what we include in the event log that I just mentioned previously. The time event is basically points to the previous event. It has a proof, which is described here, and has a path. And so the proof is basically this object, and it points to the root, and the chain ID, which basically points to, like, hey, which blockchain is this proof on? So in our case, it's the Ethereum mainnet. Transaction hash, which is basically the hash that was included in the blockchain, and type, basically describing how we can go from the smart contract to retrieve the CID of the Merkle root. And the path here basically describes the path in the Merkle tree that you need to take to verify that the prev here, like the previous event CID, actually is the same as the one that's pointed to from the blockchain anchor. So if we go back to this, we can see that these time events have this proof metadata that is talked about, and the blockchain transaction basically through the Merkle tree points back to the previous event, which should be the same as the previous event from the time event here. And this is actually also a standard that's standardized within the Chain Agnostic Standards Alliance. So you can go and read, I think it should be called CIP 168 or something like this. I'm not sure why I didn't include that, the name of that in here. But yeah, so this is not something that's ceramic specific. It's actually something that we try to standardize that other people can use in their protocols. All right, so finally we get to data synchronization. So in a protocol like this, we want to be able to synchronize one event log if we want user-centric data. So a user comes to the application, they write a bunch of data, they want to be able to have that data, not only in the application, maybe in another application or in their own local machine. I should be able to synchronize only my own data. I would also like to be able to synchronize multiple event logs. So there could be a group of users that maybe are editing some information together. And finally, we also probably want to be able to synchronize all of the event logs. So that could be like an application that just want to have an index of all of the data that the application has generated over time. And to solve this problem, we've implemented something called Recon. And so this is based on a paper called range-based set reconciliation. And essentially takes the approach of splitting all of the events into an ordered list, and then allowing you to synchronize any subset of that range. And we've implemented this as a sub-protocol for libp2p. And this essentially allows us to synchronize any growing set of data that is authenticated in the way that have this like self-certification property. And in practice, what it means for Ceramic is that we can select data based on essentially schemas of data models. So if your application has a specific data model, you can synchronize only the data that's relevant to your application. And you can even like shard that arbitrarily as your application grows. So just to give you an idea of like how we sort the data, we basically have a network ID for like which Ceramic network. Is this like the main network or is it the test network? This sort is basically based on a header property in the event stream. Then we have the controller, essentially the identifier of the user that created the stream. Then an identifier for the stream itself. Height, basically like the height is basically the number of events in the event stream that have been created. And finally, we use like the hash of the event itself. So this allows us to deterministically order all of the events, not only in one stream, but across multiple streams. Actually, across the entire network, we can order all of the events that have ever taken place. And so let's look at how this protocol actually works in practice. So here we have two computers, two people using the recon protocol to synchronize names of animals. So in practice, what we synchronize is actually be more like hashes of pieces of data, like CIDs. But here we're just going to demonstrate syncing these small strings. So this computer has the ape, the eel, the fox, and the gnu. This computer has the bee, cat, doe, eel, fox, hog. And so this computer actually wants to get the sync. So it sends a message to the other computer that includes ape. It includes the hash of the two intermediary values, and includes the last value. So you can see like the first, the last, and the hash of the things in between. The other computer receives this message, adds the thing it didn't have to its own store, and then it sends back, basically, it splits. It sees that, okay, I don't have the same hash as this for the values, so I'm going to split the range in two and send back the split ranges. So still start with ape, but we actually stop with hog instead of gnu, and then we send the hash in between the middle value, which in this case is bee, cat, and the hash in between the other values, which in this case is eel, fox. And when the first participant gets this back, it can see like, oh, here's some new values that I haven't had added to my store, but I still can't compute the same hash. Then I split that range in half again to send values back that I don't know if the other participant hashed. So in this case, it looks like this is the values we have in between here, like doe and hog. And between ape and doe, we don't actually have any value here. And finally, now we can see like the things that are missing and send those back. And at this point, this computer seems to be completely synchronized with the other one. So we send the first value, the last value, and the hash in between. And to finalize everything, the same message is sent back. And we're now actually completely synchronized. So this protocol is really nice because it allows us to synchronize these data sets even as they're growing and mutating. And it actually doesn't imply any intrinsic data structure internally in the clients. So normally in these peer-to-peer synchronization protocols, you have like an internal Merkle tree representation to be able to like go down the tree. This protocol doesn't actually require that. This hash function that's used here is called an associative hash function, which means that, see if you can find a shorter example, which means that here for eel, fox, and gnu, if you hash eel, fox, and gnu independently and just add them together, you'll get a value. And if you do that in any order, you get the same value. And this allows you to not actually enforce a Merkle tree structure on the storage for that node. You can actually have different clients that implement different tree structures for different optimizations. In our implementation right now, we actually just have an SQLite store and do a query over that to select all the things and use the sum function in SQL to sum all the hashes together. And so this gives just the implementers of the protocol a lot of flexibility, which is really cool. Yeah, our implementation of this right now is based in Rust. It's based on an implementation of IPFS called Beetle, which the IRO team implemented earlier before they moved on to like a completely separate code base from IPFS. And the reason we're doing this is we're trying to migrate away from, right now, Ceramic has an implementation on, based on Kubo and based on a JavaScript client that talks to that. We want to have more control over the libPDP layer, and so we actually have now like implementing this Rust layer. And right now we're sort of mirroring what Kubo does, but we're actually going to remove probably the function in IPFS that like publishes every object to the DHT, because that's not super efficient, and instead just like rely on this recon protocol to synchronize data across the network. All right, so to recap, Ceramic actually provides EC authentication because you can natively support wallets that is being extended to support things like passkeys, potentially things like Passport in the future. I think that would be super cool. We're also looking at ways to author data based on on-chain Ethereum state. So for example, one thing that we're getting a lot of requests for is basically having smart contract accounts author data into Ceramic. And so there's various ways of basically taking chain state from Ethereum, creating a Merkle proof of the state of Ethereum, and using that as an object capability inside of Ceramic. So you basically delegate from on-chain to a session key by just looking at the state of Ethereum. And since we do this timestamping, we can enable key rotation and tamper resistance. Basically, if, the example I mentioned before where the object capability, the session key was only valid until 5 o'clock. If I author it now and it get timestamped before now, it would be considered valid. If I author it in an hour from now and timestamp it, there's no way I can like timestamp things in the past, because then I would need to attack the entire Ethereum blockchain. And finally, we have this neat recon synchronization protocol. All right, so how can you use these primitives that we've built? And so right now, like we've built a protocol on top of Ceramic called ComposeDB. Essentially, it's like a GraphQL database that you can use to like build fairly feature-rich applications. But we also want to separate this like database system we built from this lower level event streaming system, and essentially enable other people in the ecosystem to build different types of databases. It would be super exciting to see this event streaming interface being used, not only to build this type of larger sort of, ComposeDB is basically aimed at like applications where you store all of the user's data in like sort of one big index. It would be cool to see people experiment with more peer-to-peer databases based on this event log structure, where you basically synchronize state between browsers. And I think you can build these sort of databases on top of Ceramic. But right now, we're basically focusing on this specific use case. But since we have this vision of like other databases being built on top, we're separating Ceramic event streams from these database indexes. And so we're in the process of designing a new API. It's called the Ceramic API. And you can comment on this API on CAP 137. And yeah, any type of feedback would be very appreciated. All right, thank you.
Hi, I'm Joropo. I work at IPFS Shipyard, which will exist very soon, okay? That's a process. So I want to talk to you today about the thing, like, I wake up in the morning and I'm like, this has to change. The world has to change. People need to know about content addressing. I think many applications would benefit of lots of improvements if they could use content addressing in the workflow. And so I want to go through, like, here's Bobby. He wants to make an app, okay? And he has a very usual problem, which is he wants to store medium size of data and a large one. The main way we're gonna see about it is like, hey, I have a profile picture. And it's on the edge of, like, you could just send it in the request. That would work, but it's slightly expensive. Like, now your RPC server has to handle the data, moving the full image. You probably want to use a cheaper CDN for that. There's no caching, so like if I update my bio, I have to refetch the image, which I don't like it. So usually the solution people come up with is, I'm just going to take my file and put it on the server and put the URL of the server. And I think it's not great. Like, it works, but it has high coupling. Like, now, if I want to change the server, I have to update my URL. And you think, oh, that's easy. I can just like write a migration. But like, if this is not just an RPC server, but this is a smart contract, now you have to update the URL on all the smart contract. It does not. It's not very good. You should be able to do caching, and like there's ETag for it. But if you tried using ETag in the real world, it's slightly annoying, and not everyone gets it right. And there's no horizontal security. Like, if my CDN gets hacked, I can have very bad images on my website, and I don't want that. So I think the solution we should use is we should put hashes here. So this is a CID. This is the term we use in IPFS. It's basically a hash plus a tiny bit of metadata. And what does that bring us? So the easiest way we could think about this is, I'm going to take my data and hash it. And that means that, and that already exists on the web if you want to use it in browsers. It's called sub-resource integrity. But I don't think it's great because it lacks many features that makes download useful. So the first one is like, if now I'm not just sending one image but a video, the video could be very big. And due to the way the hashes work, we only have the hash at the end of the file. So if I want to download from the start to the end, I will only know if I got like 1 bit of data wrong, and I will only know that by the end. So if I download 20 gigs and I have to throw it all away, very bad. So what if we use like Merkle tree? It's a quite basic crypto construction of, instead of having the hash of the full file, I have the hash of this special thing on the side, which lists all the hashes inside the file. So we have hashes and offsets. And that means that like, if my user 6 at a random point in the video, I can just download the topmost block, I verify it, I know that it's valid, and then I can jump in the middle, and I don't have to download everything else. And that means incrementally verifiable, because as soon as like I get one of the blocks on the bottom, I can already return the data to my user. I don't have to download all of it. And okay, I just said we should use hashes because we can use content verifiability, but it's not the only thing. We have to couple it with something else because like I cannot contact a hash on the internet. It's not really a thing. IP works on internet addresses. So the usual, like, nice way to do it is to use DHT. The way we do is like, we have a bunch of nodes on the network that wants to figure out where files are. And so these are going to run DHT servers. And it's organized in a way where you sort them based on the public key. And then once I want to publish a file, someone will need on the DHT to remember that I have this file. And so I start like at a random node because I don't know the full network. And this random node will know some of its neighbors, and it knows less far away as you go farther. And so the first node will tell me like about a second node that is closer. The second node will tell me about third one, and the third one it doesn't know anyone better. That means that in this DHT key space for the particle CID, the node on the bottom right will be the one that has the file. And then when someone wants to fetch it, it comes later. It can start at a totally other different point in the DHT, and it's going to converge through a different path. It's going to find the same first node, and at this point, right here, the node remembers that the publisher stored this file. So when I want to download it, it's going to tell me, hey, you can go talk to the node that originally had the file. And it allows us to find us on internet to download files. And you might think like, okay, that's an extra thing I have to do, but we're already doing that in the previous example of location addressing. Even though we do it through DNS, we have like a similar recursive process. It's hierarchical instead of being based on the sorted key space. But it's similar, like I asked various people and they're gonna tell me at the end who has my data. So a last solution that we often see is indexers. And for example, on IPFS, we have IPNI, Torrent has tracker. So IPNI can work in that way, where the publisher sends to a PubSub channel a list of CID has, and the CID.contact, which is a database, is going to ingest it. And then later, the client can just ask CID.contact or some other indexer. And the point is, if you have a large amount of data, it's cheaper than using a DHT. And so at this point, like, we just did magic. Like, it doesn't look like it, but we really did magic, because now we can do many interesting things. So a random example I'm going to show of why I think this is superior. Torrent, for example. People tell you that usually, if you want to host video on internet, this is going to cost a lot. Like, a lot, because you have a bunch of transit costs and stuff. And I don't know, but like, there's a website with more or less legal videos, and they don't seem to have lots of money, and they work fine. And quite basic usage is that when the user downloads a video, they're going to reshare it with other people. So you can, that really helps you on the cost side, because people contribute to the cost of, like, I download a video, I contribute to the cost of downloading it because I will reshare it for the next people. It's more resilient because I can have thousands of nodes. And actually, Torrent is faster than HTTP in multiple cases, because like, I have fast fiber, very fast fiber. Europe is nice for that. And most HTTP servers are slower than my fiber. But with Torrent, I can just ask more and more and more nodes. And it can scale very extremely well if the file is popular. And the first interesting thing to note is, like, thanks to the two properties of content addressing, which is I can verify my data, and I can, I'm using the hash to figure out who I should contact, and I don't include that directly. I was able to download data from strangers on the internet. And if you want, like, the highest possible throughput between a few people, Torrent is probably the best solution you can have right now. Another interesting one is Git. So Git was created by the Linux kernel because they were solving the problem of, hey, we have hundreds and thousands of teams, and they need to talk about the code. And so the interesting thing that Git does is, because Git, you have seen, like, probably Git hashes. I can show you one at the end if someone has questions, but it's a hash that points to a position in the source tree. And so if I need to share a bug with someone else, I don't need to say, hey, you need to check out the branch on this server at, like, this hour because I might modify it later. No, it's like a hash is fixed. It depends on the data. So if I were to change it, the hash will also be different. And it's a really good properties because on Git, they don't have, on Linux, they don't have, like, one central server that everyone uses. There's a big one, big Git server, but also teams can decide, hey, I would rather have my branch be on GitHub, and I'm gonna pull it from time to time back to the main server. And, like, it doesn't care how you got the data. It just, you have the right hashes, it matches, that's all I care. And so it's, like, really good property of, I want to talk about data. I shouldn't say, oh, but your data really has to come from, like, that server over there, and you need the valid TLS cert, and, like, no, I just tell me what data I should have, and if I have it, it works. And the last application I found very good application of content addressing is Docker. Docker has, like, this problem of Docker images can get quite big, and most of the data is similar. And so using content addressing here makes caching very easy, because if I ask you about a layer, so Docker works in layers. So, like, I can start from a Linux layer. I can add the Go layer if I want to build a Go app. And then on top of that, I'm going to have a layer for my own application. And if I want to build, like, 2 different Go apps, it would be very annoying if I have to figure out that, like, actually I can reuse the previous version of Go because the version matches and stuff. No, so you can do that very easy because you know all the hashes of every layer. And if the hash match, then you know the data has to be correct. There is no way for the data to be incorrect if the hash matches, unless you use a broken hash function, but we use Shadow56, and thankfully it is safe for now. And that means that you can deploy your own Docker caching layer somewhere on your data center, for example. And if you have many computers, it's going to be way cheaper than downloading it from someone else that's going to send it to you over expensive fiber. So interesting use case of like, hey, we have hashes that makes caching way easier. And so where does IPFS fit into that? I think the main problem with the free lattice solution I've talked about, and also content addressing solution, is that they're very snowflake. Like someone wanted to solve a problem, and they're like, let me make content addressing from scratch. And I don't think it's great because it's annoying for people to use. Like if I want to store my Docker layers on Filecoin, let's say, because I don't know, I heard Filecoin has cheap storage, it's going to be very annoying to do because I cannot easily, like Filecoin speaks a different language than Docker. And there's an opportunity cost in the same way that like, maybe the application that would work if we could have, I could take Docker and I could put it on torrent. Like that would be awesome. Like I would have peer-to-peer. There's this expensive Docker Hub subscription I need to fetch my Dockers. Like why can't I just fetch it from someone else that would happily reshare it for free to me? So if we were sharing like some basic protocols that we could all speak and work together with various implementations, wouldn't that be better? Like I would have Docker and torrent and I could do and mash them together and like, I don't know. But basically the point is, that's why we're trying to do IPFS. So how are we doing it? Primitives, important. So CID is the one I was showing earlier. It's a way to describe pieces of data. We write specs with the goal of multiple implementation having them supported. On my team, we do Boxo, which is a library for people to reuse and work in their own content address application. So again, like if you want to make your own content address application, you shouldn't have to restart from the beginning. I don't think it makes a lot of sense. So we have libraries. There are other people like Iro and Nabu, or I don't know the list. And so the last thing is actually getting stuff into web standards, browsers, and other applications. So there's like a huge difference between I can write a patch for a browser that works, but getting it merged and adding new features is a completely different process. It's very hard, and we have people that have experience to that. So we're really trying to change the world in the sense of like, kind of, you could say it's a bit limited, but I think the applications are pretty good. And so why don't we have IPFS everywhere? If we like, that would be good. I could have faster downloads, cheaper storage. Why doesn't that exist everywhere? I think the main issue I heard about the time is like trade-offs. And it's interesting of like, you don't need to be better, but you could be way better on other points, and I still gonna hear people tell me, oh, but like in that point, you're slightly worse. So it's kind of like a thing. I don't see any reason why just using IPFS, we need to be slower than other things, except no one put in the effort to do it yet. So HTTP is faster. Well, now we have HTTP on IPFS. If you like HTTP, there are various specs and issues of specs we want to write that could help you on that. But torrent is faster. Iro has showed up pretty good numbers that they are at least just as fast. I have some piece of code, soon TM. I don't have I need to work on it, but it takes lots of time. So the browsers is like a huge piece. And it's interesting to work on adding support to browsers, but this is a long effort. And like, even if that happened, you sometimes often want to use new features. So why do you have to wait like for a new feature to show up? Can we just not give you the thing directly in the browser? So there's Kilia, JavaScript implementation. And you would be surprised of like how much Go and Rust code can be compiled to WASM and run in the browser. This is very good. And like the thing I probably heard the most is that IPFS is like a resource hog. And I would say like, no, it's not. It's Kubo is a resource hog, which is Go IPFS, which is the main experience a lot of people had with IPFS. And if you try this other somewhat IPFS implementation, you're gonna find that like, no, it's fine actually. A last thing I would say is like what I think is missing. There's this new implementation which is called Iro. It's pretty good, I hear. The implementation is great, but they stopped being intercompatible. And I think we could have quite easily intercompatibility with Iro, not with all the protocols, but make me be able to fetch and receive Blake-free. So the protocol for Iro is some stream request response, and that would map very cleanly over the trustless gateway API specs. that we just wrote and shipped in Kubo. So that would be nice if like, then other applications, then IRO would become back in the IPFS ecosystem and be compatible with other storage layers. And I have a list of good reads if you want to hear more about it. And I was thinking, as a conclusion, like, I think it would be cool to show, hey, we should make an IPFS implementation right now. So I'm going to do like the most basic thing, but a bit of live coding. Yeah, I tried doing something more complex, but it didn't work. The demo god was not on me. So let's try something. I'm going to try to verify files from IPFS, and I think we should be, oh, it already exists. Is that good enough? Okay, a lot better. Well, I'm going to call it F. So the goal is, hey, I want to fetch data from IPFS in like few lines of code that's possible. So basic go, oh, need to. How do I make that go away? Okay. So I'm not going to bore you with the details. Sorry, it's Go. So the first thing I would use is a thing I just wrote. It's not merged yet, but it's going to be soon. So we want to use the new gateway API because it's very cheap and easy to use. So, oh, I see my LSP is not working because thanks. So what if, so I'm going to create a new client because I need a client to download thing. So, okay, really, my LSP really not working. I really have to think about it. Oh, now LSP. Okay, I needed to save. Great. So I'm going to use a static gateway. I tried doing the content routing with the DHT earlier, but DHT is not happy on that network, and I don't know why. So we're going to cheat a tiny bit. So I'm going to download from IPFS.io, but it's still going to be trustless and verified. So if IPFS.io were to lie to me and send me bad data, I will catch it. So I have a client now. I need to check errors, and as you know, if you return Go, checking errors is annoying, so we're just gonna handle the error. It's handled now. Now I want to get my file. f.download, oh, client, sorry. I need to parse it, CID must parse. I have some other CID I meant to try. I should have it somewhere. Where do I have it? Oh, I know where it is. Sorry, it's gonna Tmax attach. Yeah, right here. That's, oh my god, it's not full. Tmax is making it annoying. Okay, great. That's the CID I wanted to try with. So I can be back right here. So because it's Go has types, so we use types because pretty good. So I just need to convert, like this is the string representation of a CID, and I call must parse on it, which will parse it. So must parse, called parse, but will panic on error. And parse, oh my god, yeah. And parse called parse generic, which is gonna implement, it's gonna do multi-base. So, yes, that's the magic thing. Okay, we don't want to look at that. The thing it's going to do, it's going to figure out that, oh, I gave it a string, and it's not /IPFS/, and then it's going to look at the first character. That's going to tell it the multibase. Once it decodes the multibase, so once it figures out the multibase key, it's going to run it. This is base 32. And once it parses the CID, it's going to extract 4 fields. The version, which is going to be 1. The codec, which YBay, I think that's UnixFS file, DACPB. And the hash function, and lastly, how it's called. The hash function, hash length, and the actual hash that we want to verify. So handling errors, don't write, you should do something better with error, but like, I'm not gonna do it, so. We need to call close because this is gonna be a streaming thing. And lastly, we want to do io.copy to os.std out. And file. And I don't have OS. It's gonna, let's see it. So great. So now, hopefully, if I'm lucky, I do go run, I pipe it into FFFplay, and it should show up. And it didn't because, my bad. HTTP, oh no, NZ. yeah, I have proxy on this, and like it's not working right. And now, hopefully, there's like a 10% chance it works. No more. Oh, it loaded. So it's been a thing we're trying to do with Boxo of having it way easier to use and do the stuff you care about. So Boxo is like organized in various puzzle pieces. And like the puzzle pieces I just use is Feather, which implements UnixFS in a very lightweight, and it's streaming, so we can see that I don't have downloaded the full file and that I'm able to see the video. And so it's kind of one of the things that's like important is you want to have great tooling for users, and I think this is on the, like this is good enough for most people. Maybe I'm wrong. If you think I'm wrong, tell me. But like have this quite basic interface. I create a client because of boring Go stuff. I need to have a place to put variables. And after that, I'm just, I do the thing I want to do. So I want to download a file, client.download file. And not all of Boxo is like that already, but we are aiming at making it better. We improve it all, every day. The gateway, for example, in Boxo was a huge part of the work while we also did the gateway specs. And so it's the end. Does anyone have questions? Steve.
Thank you. So Feather, I'm assuming this is doing verified retrieval, and does it have the ability to support multiple gateways to pull from to get more of the BitTorrent experience you were referencing?
So if you ask me in like a week, it will. Right now, you're right, it doesn't, but it's not the very hard part. Like I can, this is gonna be hard to read, but the Feather code is basically, there should be a read method somewhere. Just passed it. So supporting multiple gateways is not that hard. We can have like a basic check of, if a gateway is not working, I just switch one. You can also run multiple gateways in parallel and take the blocks from the fastest one. The hard part is like if you want something that's both efficient and fast, this is hard to do. But I think we should have something like that's 95% of the way there in Feather. And the main point of Feather is that it's very efficient. It's very light. Like the whole implementation is 300 lines of code. And I write lots of lines of code. You could make it way shorter. So I hope it answers the question. Any other question or?
So I hope I'm in the right talk, but this was why IPFS content addressing is the second best thing. What is the first? Is that Feather?
I don't know about the first. The point is you can decide yourself. You have to be creative.
Sweet. Okay, thanks.
Well, thanks for coming. We have a closing talk soon. I think it's in the room over there. Cora. You say 6? Maybe, I don't know.
Okay. I could do the HDMI. Actually, I have HDMI on this one. Amen. Amen. Yeah. Nice to meet you too. Mary. Yeah. Okay. Okay. Awesome. Okay. Hello, everybody. All right, so this is fun. Being the last speaker, I mean, it's a lot of pressure here. And especially to follow up with someone who did live coding. I'm actually going to do the same thing here. I'm going to live code. But let me tell you a little bit about ThirdWeb. First of all, my name is Eamon. I lead solutions at ThirdWeb. What is ThirdWeb doing at an IPFS conference? What we're trying to do as a mission as a company is we're trying to make Web3 development very, very easy for developers. You don't have to be a Web3 developer. You don't have to know all of the nitty-gritty of any of these protocols. We just make it easy. You could be a Web2 developer to do that. And what that entails is we provide a full stack for people. You know, everything from, oh, you're looking to onboard users. Well, you need wallets. Oh, you need payment rails. You need to do fiat. You can do that. We have smart contracts. And maybe the most important part here is that what we also do is we also provide infrastructure. And part of what we try to do is also leverage decentralized storage as much as we can. We use it both internally in our smart contracts. So for things like how we decide to store our Merkle roots for our NFT drop contracts, we load that onto IPFS. You know, the obvious use case that people use is when it comes to the media associated with NFTs. But that's who Third Web is. So what I was going to actually do is I'm going to build a really, really quick dApp for you. And what at the conclusion of all of this, I am going to deploy it to IPFS. So it's actually like I'm going to create really like I'm going to craft a Web 2 experience where someone would be able to mint an NFT using an embedded wallet, all of that being deployed to IPFS. And I'm going to try to do that as fast as my esteemed presenter right before me did. No? You think? Are you saying that he's probably saying that, you know, the bar isn't that? But let me show you what we mean when we say to make things easy. So we have a CLI tool. If I want to create a Web3 application, it's as simple as me just saying npx third web create app. Oh no. Sorry. I don't think you guys want to see me download the latest version of our CLI. So let me just get rid of that. No reason for me to do that. Okay. Oh, you know what? Sorry, you're going to have to do that. I apologize. This is where I give demos all the time. I run solutions, so I work with customers all the time. This is where I have really good filler material as something is being downloaded, but this hopefully shouldn't take that much time. With our CLI tool, you can create apps, you can create custom contracts. We have a Solidity SDK. And really what's going to happen here is essentially we're going to download all of the scaffolding for whatever type of app you're trying to build. All I'm going to do is I'm going to build a web app. Look, you guys are here. You guys trust me and believe me that that's the case, because really what I'm going to do is I'm just going to go right to VS Code, because I didn't want you all to see me have to code every single piece of this. This is what you get. If I go to npx third web create and I say create app, in this I can pick my framework, everything from React to Next to, in my particular case here, I'm using Vite. And essentially what it does is it just has given me the scaffolding, right? So let's start with, you know, when you're building your app, what you have is you have something called a third web provider. You just wrap your third web provider with whichever EVM chain you want to connect to. So what I'm going to do actually here is I'm going to, so what I'm going to do is we're going to craft the onboarding experience. So we have this little playground, like a sandbox, where what you can do is you can create your own, think of it as like a Connect wallet experience. So what I have here is I can customize everything here. I can choose between which Web3 wallets I want to have included. We support a whole bunch of them. If I want to have embedded wallets, which I do, which, you know, has social and email login, that sort of thing. You can create like guest wallets if you're a game. So think of it as like, I just want to create a local device wallet. All of that is just like, you know, parameters that I set up. And as you can see here, as I set things up, all it's doing here is it's generating code for me that I'm going to cut and paste into my application. So you know what? I want this to be very Web 2 centric. So I'm going to change my Connect wallet to be, you know, choose your connection method, right? You know what? I don't like these third web guys always putting their logos. Oh, I want to change the splash image. So what I can do is on our third web dashboard, this is, we provide storage infrastructure, like I told you. So we have like just a UI here in our dashboard where any user can essentially upload and pin their assets. So, you know, my image, since this is Dev Connect, what I'm gonna do here is I'm just gonna drag and drop this, and I'm gonna upload this to IPFS. It's there. Now I can just grab my hash. I can go back to where I was crafting our experience. I can do Control V, and there's my image. I can say, you know what, this is at IPFS Connect. I think y'all get the idea, right? What I'm gonna do now is I'm gonna kind of do some cutting and pasting. So I'm gonna take, you know, the first thing I'm gonna do is I'm gonna take my third web provider and I'm gonna go back to our code and I'm gonna override that. What I'm going to want to do as well, I don't need you, actually. Okay, and then, you know, in honor of Arbitrum Gurley going away and being deprecated here in the next couple of days, instead of connecting to Ethereum, let's connect to Arbitrum Gurley. We have a chains package, so I can just, it's as simple as me just taking this, replacing my chain ID with Ethereum to Arbitrum Gurley. Great. Oops, I need my client ID. Luckily, first I'm gonna do this, and I'm gonna say, sorry, active chain, and then here, yep, you know, this is, I'm gonna do import.meta.env.vite template. Client ID is the name of my variable. Okay, that's it, I'm done. So now this is essentially going to my wallets. These are the supported wallets in my application. I'm basically set up to connect to any EVM chain. In our case, we're gonna go to Arbitrum Gurley. So the last piece of this then is the connect wallet button, right? And so I'm going to go back to my app here. I am going to grab this beautiful connect wallet that you all saw. I'm gonna cut and paste it into my, okay. And then the last piece of this is I want to put like a button just for being able to claim my NFT, right? So what I can do there is I can use our hook, use address, which is basically like the wallet address of the connected wallet, whatever the user decided to connect. That's the easy part. And then I come over here and tricks of the trade here for those of you who want to do live demos. You just do this and you uncomment it so that people aren't bored with what you're doing. So you can essentially see here that what we provide is a little component called a Web3 button that you can give it a contract address, and then depending on the type of address, you can make a call for that. All right, so where am I going to get the contract from? We're going to go back to the third web dashboard, and what I can do here now is if I go to contracts, and that's not good, I go to contracts, and now I connect my wallet to the dashboard because I'm going to be deploying here. I can go to deploy contract, and now this is like just a registry of smart contract templates, audited smart contract templates that you can deploy to any EVM chain from our dashboard, 100% owned by you. What I'm going to do is I'm going to go back to Explore, and I actually want to grab an open edition. We're just going to do an open edition here. And so I'm going to deploy this guy. I'm going to call it my IPFS Connect NFT. I can upload an image, which, yes, you guessed it, folks. It's going to be automatically uploaded to IPFS by our application. And so when I deploy this contract, you'll see my MetaMask get prompted here. And it's essentially now all I have to do is set up my contract. So we'll do that real quick. So we'll deploy the contract. There's some other kind of setup that's happening here related to the NFT metadata. And then one last step here, which is, you know, basically a signature so that this contract will be added to our third web dashboard. So once this completes, we'll have our contract address. All I'll have to do is I'll just have to plug that into our application. Come on, Arbitrum Girly, come on. I know, probably sad, waiting for us to deprecate it, so it's not cooperating. But once this returns, is it? Did I not sign it? Let's see here. Oh no, I did sign it. Okay. Wonder what is happening. Okay, what I'll do here then, rather than trying to debug this right now, what I will do is just use, I'll just use an existing contract that I have on Arbitrum Girly. So I'll go back to my dashboard. I'll just pick from Arbitrum Girly, and let's see here. Yes, I have an open edition here. So I'll go ahead and use this one, right? So it's been set up. So essentially what I did is I've set up my metadata for the NFT, and then the other thing that I've done is I've set up my claim conditions. The claim conditions are what I described to you, which was essentially allow lists and the Merkle root. So what I can do now is take this guy, and I can go back to my app, I can plug it in, and that's it. And so we're basically ready here. What I can do here is I can say yarn dev, run my app. Let's go ahead and load it. And here's the application, right? I can sign in here. I can choose between different social logins to log into the app, and I'll be able to claim my NFT. So the last step here, which I told you about, is like, okay, that's cool. We tested it. Looks like it's working. Everything is like it is. I can go back to my CLI tool, and I can just say deploy. I can say app. And so what this is going to do here is essentially build. This is going to build the project and then deploy it to IPFS, returning basically like the IPFS hash. And at that point now you can put that into any IPFS gateway, and when you load that, then what you'll have is you will have a running application running on IPFS. So let me make this a little, oops, sorry about that, here. Okay, so you can see here that it was built, 15 seconds. Here is my hash. So if I go ahead and load that into IPFS, you can kind of see here that our app is loaded and it's running here. And so I can run it the exact same app that I was talking about there. So I think when I made the title of this, I said it was going to be in 15 minutes. I don't know. Oh, I actually did make 15 minutes. It's 5:14. So I actually did all that, explained who ThirdWeb was, and showed you how you can do that very, very easily using our tools. Any questions from the remaining people? Cool. All right. Well, thank you all for sticking around at the last session. And if you have any, if you're interested in ThirdWeb, it's thirdweb.com. If you go to our dashboard, it's thirdweb.com/dashboard. Thank you.
Do you want to stop the YouTube streaming?